This section is about trees. So we'll learn about general trees and binary trees and various types of binary trees. So in this video, we'll learn about the terminology of trees and introduction to binary trees. So let us start with terminology. See, here I have taken a general tree and nodes are containing alphabets so that it's easy for you to understand. Let us define a tree. Tree is a collection of nodes or vertices and edges. Nodes and edges. These links are called as edges. If there are n nodes, then there will be n-1 edges. Because for each node, you can see that there is an edge coming over that node. There is an edge coming over that node. Every node, there is an edge coming from its parent. Except root. Root is not having a edge coming from any parent because that is the parent of all the nodes. So if there are n vertices, then there will be n-1 edges. This is a root node for the tree. And if I look at only this portion, all the nodes below B, then this is a subtree. D and all the descendants of D, all the nodes below D is a subtree. So if I define a tree, tree is a collection of nodes. Among those nodes, one node is taken as root node. Rest of the nodes are divided into disjoint subsets. They are in subset. This is one subset, this is another subset. There is only one node in this subset. And each subset is a tree again or subtree again. So I repeat the definition. Tree is a collection of nodes where one of the node is taken as root node and the rest of the nodes are divided into disjoint subsets and each subset is a tree or subtree. Now let us look at the terms. First, root. The very first node on the top is a root. Parent and child. A node is a parent to its very next descendants or those children which are connected with just one edge or those descendants which are connected with one edge. So for B, E and F are its children. For D, G, H, I are children of D. So D is a parent of G, H, I. N and O are children of L. L is a parent of N and O. So we have finished these. Now siblings. Siblings are children of same parent. G, H, I are children of D. So they are sibling to each other. G, H, I are siblings. J and K are siblings because their parent is same. N and O are siblings. Next, descendants. For any node, the set of nodes which are its children and their children and their children, so on. Or in other words, descendants are all those set of nodes which can be reached from a particular node or under that node. For example, for B, E, F, J, K, M, all these are descendants of B. For L, N and O are descendants. For D, G, H, I, L, N, O, all the nodes that are reachable from D, descendants of D. Next is ancestors. So for any node, all the nodes along the path from that node to root node. So for M, J, F, B, A are ancestors. For N, L, H, D, A are ancestors. The next is degree of a node. Degree of a node is number of children it is having, direct children, not all descendants, direct children. Degree of L is 2, it is having 2 children. Degree of D is 3. Degree of A is 3. Degree of F is 2. Degree of J is 1. And degree of N is 0. K is 0. M is 0. Number of children any node is having is the degree of a node. Then what is the degree of a tree? From the tree, we cannot tell what is the degree. Degree is pre-decided. But if you observe, what is the maximum degree of any node? 3. See, this is having 3 degree, this is having 3 degree. So, the degree of a tree can be minimum 3. Minimum, at least it is 3. Or it is more than 3 also. So, I can explain you afterwards. Then coming to Internal nodes and external nodes. Internal nodes, external nodes are also called as non-leaf nodes and leaf nodes, or terminal nodes or non-terminal nodes. What are those? Nodes with degree 0 are called as leaf nodes. Degree 0, degree 0, degree 0. So E, M, K, G, C, N, O, I, all these are leaf nodes or external nodes or terminal nodes. And those nodes whose degree is greater than 0 are internal nodes, non-leaf nodes, non-terminal nodes. Next, levels. See, level of a tree starts from 1 onwards, that is root is at level 1, then its children at level 2 and their children at level 3 and 4 and so on. So level starts from 1 onwards. So actually for level we count nodes. Here one node, horizontally if you see there is one node. Then at this level if you come, total 2 nodes are there. Either you count this 2 or this 2. We don't count all nodes, just the path. In the path we will count 2 nodes. Until here the path from root, that will take 3 nodes, 1, 2, 3. Either you come here or you come here, anywhere. At this level there are 3 nodes, 1, 2, 3 nodes. Then at this level there are 4 nodes, 1, 2, 3, 4 nodes. So we take the path by taking number of nodes. So that's how it is levels. The next is height of a tree. Height of a tree I will mark it here on this side. Root is at height 0 and its children at height 1, then height 2, then height 3 and 4. See, here we count edges. Till here there are no edges. Now if you come down to this next level, or let us say level only, or path, either you go here or here or here, then how many edges are there? One edge is there. So this is taking one edge to reach here. One edge to reach here at this horizontally at this level. 2 edges are there. So 1, 2, 2 edges. Then till here 3 edges, then 4 edges. So level starts from 1 onwards and the height starts from 0 onwards. Height and level both are useful for analysis. Now coming to the last term, that is forest. A collection of trees is called as a forest. For example, here I will make a change. I have removed A, root I have removed. How many trees do you see? This is one, then this is just in single node tree and this is another. Total 3 trees are there. So this is a forest. Collection of trees is a forest. And if at all you want to make it as a tree by combining all the forests, then you can introduce a node like this. So here a forest is converted into a tree. So forest is collection of trees. So that's all with the terminology. Now I will introduce you to a binary tree. Now let us learn about binary tree. A tree of degree 2. Degree 2 means every node can have maximum 2 children, not more than 2 children. It can have less than 2 children, but not more than 2 children. So degree of a tree must be 2. If the degree is 2, then it is called as binary tree. By 2. So 2 children. So every node can have 2 children. A is having B and C. B is having D and E. Likewise, C is having F and G. As there are only 2 children, we will give the names to the children. This is left child and this is right child. So for B, this is left child and this is right child. So we give names as left child and right child. One more definition of a binary tree, that every node can have either 0 children or 1 child or at most 2 children. So children can be either 0, 1 or 2, not more than 2. Let us look at some examples of binary tree. I will draw some binary trees. I will not label them. This is labeling A, B, C, D. Just I will draw dummy nodes and look at the shape and find out whether it is a binary tree or not. Here I have some binary trees. First one. Is it a binary tree? This is not having any children. Yes, every node can have 0, 1 or 2 children. How many children is it having? 2 children. Okay, perfect. How many children? 0. Perfect. 2 children. Perfect. 0, 0. Everything is perfect. What about this? This node, 1 child. Yes, perfect. 0, 1 or 2. Remember this. This node, 1 child. Okay, perfect. This node, 0 children. Perfect. This is also a binary tree, and this type of tree is called as left skewed tree. So this is left skewed binary tree. And this one, this is another one. I'll just put a separation here. That is another one, third one. And that is also a binary tree, that is right skewed binary tree. What about this one? How many children? 3. No, this is not a binary tree. So when do you say it's not a binary tree? If any node is having more than 2 children, then you say it's not a binary tree. Less than 2 children is not a problem. So this is a binary tree, this is a binary tree. This is not a binary tree. This one is not a binary tree. Then what about fifth one? See this tree, just rotate it with some angle. This is same as this one. Yes, we draw the tree like this also. Instead of drawing left right child, we draw down and right child. So this shape is also possible. So we draw a tree like this also. So binary trees are more commonly used. There are various forms of binary trees. We'll be learning them slowly. So in this video, we have finished the topic. I have discussed the terminology and introduction to binary trees. The topic is number of binary trees for a given set of nodes. It means if suppose some number of nodes are given, like 3 nodes are given, then using 3 nodes, how many different binary trees can be generated? We are going to learn that. We will learn about 2 types of nodes, that is unlabeled nodes and labeled nodes. Let us start with unlabeled node. This is an example of unlabeled nodes. These are empty nodes. Labeling is not there. Alphabets A, B, C or numbers 1, 2, 3, nothing is written in that. So these are unlabeled nodes. So if 3 nodes are given, how many different binary trees can be generated? I will draw them and show here. This is one shape, first one. Second shape, that is root, left and its right. Third shape with 3 nodes. Now next will be a mirror image of this one. This is the fourth one. The next will be mirror image of this. There are 5 different trees. So if there are 3 nodes given, number of trees, if it is a function, then the value of this function is 5. So if there are 3 nodes, we can generate 5 different shaped binary trees. 5. 1, 2, 3, 4, 5. Next, if there are 4 nodes, then how many different shaped binary trees can be generated? So I'll take 4 nodes. Number of nodes are 4. These are 4 unlabeled nodes. I will draw different shaped binary trees here. So here I have generated few. Look at them. First one, second, third, fourth, fifth, sixth, 7. I have drawn 7. Then I can take the mirror images and I can draw 7 more. This is one shape. So this is left skewed. Then also I can have right skewed. Right? So for each I can have a mirror image. So 7 more I can draw. So I will complete that. Now I have all 14 trees. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 different shapes of binary trees. So it means if number of nodes are 4, then we can have 14 different shaped binary trees. So for 3 nodes, we got number of trees as 5, and for 4 nodes, we got the number of trees as 14. Then for 5 nodes, how many it will be? For 6 nodes, how many it will be? Shall I draw every time and check them? No. Just for observation, I have drawn them. To explain you what does it mean by number of trees, I have drawn them, right? Now, there must be some formula for this one. Yes, there is some formula. That formula is number of trees for given number of nodes are 2n Cn by n plus 1. This is a famous formula. The name of this formula is Catalan number. This is a known formula. 2n Cn by n plus 1. So if n nodes are given, then these many number of binary trees can be generated. So for 5, how many? Let me calculate. T5 will be 2 into 5 C5 by 5 plus 1. This is 10 C5 by 6. 10 C5 by 6. And this is 10 into 9 into 8 into 7 into 6 divided by 5 into 4 into 3 into 2 into 1. So whole thing divided by 6. Now let us divide this and get the answer. 6 gets cancelled. 5 2's 10 is gone. 4 2's 8 and 3 3 is 9. So this is 3 into 2 into 7 is remaining here. So this is 42. So T5 is 42. So for any given number of nodes, you can find out how many different shaped binary trees can be generated. If at all you want to try out and see how those trees looks like, then you have to draw all of them. That may not be practical, so I have just shown for 3 nodes and 4 nodes. Now one more observation I have to do here. See, when 3 nodes are given, what could be the maximum height? Height starts from 0 onwards. So 0, 1, 2. So 0, 1, 2. So the maximum height possible is 2. This tree is of height 2 and 2, and this is not a 2, this is 1, 2, 2. So how many trees are there with maximum height? 1, 2, 3, 4. So the number of trees with maximum height are 4, so that is 2 square. This is for how many nodes? N equal to 3 nodes. Then what about n equal to 4 nodes? Number of trees with maximum height. Let us count them. 0, 1, 2, 3. Yes, this is maximum height because there are 4 nodes, so the height should be maximum 3. So 1, 2, 3, 4. This is not maximum. No, 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 no. Yes. 5, 6, 7, 8. So 8 trees are there with maximum height. So this is 2 cube. So for n equal to 5, how much it will be? You can guess now. 16. Yes, this is 2 power 4. So for any n, how many trees will be there? 2 power n minus 1. So we have learned how many different shaped binary trees can be generated for given number of nodes. So we don't have to generate the tree. We can use the formula. And one more observation we did. Then how many binary trees are possible with maximum height? So that is 2 power n minus 1. Now next, let us generate one more formula for Catalan number. So I will write down few values of a Catalan number. Then from that, let us see how we can come up with one more formula for Catalan number. So first of all, I will take the table of values for Catalan number. See, if n is given, then Catalan number Tn, that we know the answer formula 2n Cn by n plus 1. See here, value of n, and this is the Catalan number. So I will take the values of n and write down the Catalan number values also. See, if it is 0, then if you put 0 in this formula, you get 1. Then if it is 1, then it is still 1. For 2, it is 2. For 3, we know the answer directly, just now we saw. Then for 4, it is 14. For 5, it is 42. So for 6, I will find out using a different method. I will not use this formula. So just watch this one. I want the answer for 6. So for that, I will multiply these values. 1 into 42 plus 1 into 14 plus 2 into 5 plus 5 into 2. See, it was 2 into 5. Now 5 into 2 plus 14 into 1 plus 42 into 1. This gives the answer for 6. So the result of this one is 132. Let us use the formula for value 6 and check whether our answer is correct or not. Let us verify. T6 is 2 into 6, 2n Cn, right? 2 into 6, C6 by 6 plus 1. So this is 12C6 by 7. This is the numerator, then the denominator will be 7. Let us cancel these. 7, 7 gets cancelled, 6 2's 12 gets cancelled, 5 2's 10, 4 2's 8, 3 3's 9. Remaining is 11 into 2 into 3 into 2. So this is 11 into 2 3 6, 6 2's 12. So 11 into 12, 132. So yes, we got the correct answer. By substituting in this formula also we got the correct answer. So how I got this one? I multiplied this one with this one and this one with this one, then this 2, then this 2, then this 2, then this 2. So let us prepare a formula for that one. So this is T6, so this is T0 into 42 is T5, T5 plus T1 into T4, then T. So the T values we are multiplying, right? So T2 into T3, then T3 into T2, then T4 into T1, then T5 into T0. So these are the terms, and each term is a product of two values. So this can be written in general form. Tn is a summation of two values, T of something into T of something. So what is this? This is starting from 0, 1, 2, 3, 4 up to 5, and this is 5, 4, 3, 2, 1. So one side it is increasing, the other part is decreasing. So this is increasing, this is decreasing. So if I take I value starting from 1 to n, then I should say I minus 1, because I is 1 means first time it should be 0. And this is n minus I. So yes, we got the formula. So Catalan number Tn is 2n by n plus 1, 2n by n plus 1. This is one formula, and the other one is summation of I takes values from 1 to n, I minus 1 into T of n minus I. So the Catalan number can also be written like this. This is a combination formula and this is a recursive formula. So that's all about the formula, Catalan formula. We have got two formula. Now we have to learn about labeled nodes. So I will remove this, then I'll explain you about labeled nodes. Now let us see labeled nodes. Labeled node means these three nodes are there. Now you can see they are labeled, right? In the previously there were no labels here. They were blank. Now something is written in that. So labeling is done. So A, B, C are labels. Then if labeled nodes are there, then how many different binary trees can be generated? That's what we have to find out. So without label, already we know the answer. Without labels, there are 5, and the formula is 2n by n plus 1. We already know the formula. This is the formula. And for 3 nodes, answer is 5. But no, these are labeled. So labeled means if I pick up just one tree, this tree if I pick up, then this is unlabeled. So if I try to label it, how many ways I can label it? 3 labels can be filled in how many ways? 3 factorial ways. Let us see. Just I will label this A, B, C. And one more labeling A, C, B. Same tree, shape is same, but the labels are changed. Permutation of label has changed. So I have different ways of filling ABC, ACB, BAC, BCA, CAB, CBA. So 1, 2, 3, 4, 5, 6. So yes, these are 6 means this is 3 factorial. So one shape can be filled in 3 factorial ways. Second shape again 3 factorial, 3 factorial, 3 factorial. So every shape in 3 factorial ways. So for 3 nodes 3 factorial, for n nodes n factorial. This is the formula. So for labeled nodes, formula is 2n by n plus 1 into n factorial, because the filling of labels. So if you look at this formula and separate it into 2 parts, this part is for shapes and this part is for filling, permutation. In how many ways nodes can be filled. So this gives you how many different shapes we can get, 5 different shapes. Then n factorial gives one shape can be filled in how many ways, that is n factorial ways. So if the nodes are labeled, then this formula. So that's all, end of the topic. So we have learned number of nodes versus number of different shaped binary trees. So this discussion or this analysis is useful further in other topics. This topic is about formulas. Height versus node formulas. So what is this? If we know the height of a binary tree, what could be the minimum number of nodes and what could be the maximum number of nodes? And vice versa. If nodes are given, what could be minimum height, what could be maximum height? We are going to discuss this one. So first, let us learn if height of a binary tree is given. Then what could be the minimum number of nodes, what could be the maximum number of nodes? So already I have taken few examples. Let us study these examples. Height of a binary tree is given, height is 1. So height starts from 0, right? So this is 0 and 1. So height is 1. So in height 1, minimum how many nodes are required to reach height 1? 2 nodes. If I remove a node, then only one node, it will not be height 1. So minimum 2 nodes are needed to make a tree of height 1. then in that height 1, maximum how many nodes are possible? 1, 2, 3 nodes are possible. Now likewise, if height is 2, then for making a tree of height 2, minimum how many nodes required? 1, 2, 3. Maximum 7 nodes. Likewise, height is 3, minimum nodes these many, maximum nodes this many. We don't want a count, we want a formula. So from observation we can generate the formula. So first let us check minimum number of nodes. If height is 1, minimum 2 nodes. Height is 2, minimum 3 nodes. Height is 3, minimum 4 nodes. So minimum nodes formula will be height plus 1. See, height plus 1. So minimum nodes n equal to h plus 1. This is one formula we got. Now we want the formula for maximum nodes. 3, 7, 15. We don't find any pattern. Like there was a pattern here, height 2, so 3, height 3, so 4, so height plus 1. But 3, 7, 15, let us observe from this tree. How we got 15? We got 15 because this is one node, and in this level there are 2 nodes, and in this level 1, 2, 3, 4 nodes are there, that is 2 square nodes, and in this level 1, 2, 3, 4, 5, 6, 7, 8, 2 cube nodes are there. So this is 1 plus 2 square plus 2 cube. This answer is 15. So all these nodes when they are added, it is becoming 15. So 1 plus 2 square plus 2 cube is giving 15. So is there any formula for this one? Let me show you the formula. See, this is GP series, AR square, AR cube, so on to AR power K. So this is GP series, and all the terms of GP series are added. So sum of the terms of GP series, that is geometric progression. Sum of the terms of GP series means geometric progression series. So there is a known formula for this one. This is A r to the power of k plus 1 minus 1 by r minus 1. This is a known formula. Now this looks like GP series only. Let me write on that one. See, I have written this one, 1 plus 2 square plus 2 cube goes on till 2 power h. Then what is A in this one? A is 1. Then what is R in this one? R is 2. See, for each term coefficient A is not there. Not there means it is 1. So A is 1 and R is 2. So I will use this formula and I will write down A as 1 and R as 2. So this is A is 1. R is 2 power, what is the maximum term I have taken? H plus 1 minus 1 by R is 2, so 2 minus 1. So if I simplify this, this is 2 power H plus 1 minus 1 divided by 2 minus 1 is 1. So that is the answer. So if you take the sum of these terms up to H, then this is 2 power H plus 1 minus 1. Let us come back to this example. Height was 3. So 1 plus 2 square plus 2 cube up to 3. Height 3. So this is nothing but 2 power h plus 1 minus 1. So 2 power 3 plus 1 minus 1. Let us put the values here. So 2 power 3 plus 1 minus 1. This is 2 power 4 minus 1. And this is 16 minus 1. So this is 15. Yes, it is correct. It is correct. So that value 15 is sum of the terms of GP series. So these are sum of the terms of GP series. So these are GP series terms. If we take maximum nodes. So that is similar to this one. We already know the formula. We have used the same formula. Now we got the formula for maximum nodes. So we already have for minimum nodes. I will remove this. I will write down for maximum nodes. So formula for maximum nodes, n equal to 2 power h plus 1 minus 1. So now we know the formula. If height of a binary tree is given, then within that height, minimum we need h plus 1 nodes, maximum 2 2 power h plus 1 minus 1 number of nodes are possible. Alright. So these formulas are very important for binary tree. Now I need the formulas in other way. If nodes are given, what will be the minimum height? What will be the maximum height? Here we know height, so we found out nodes. Now next, we will be knowing nodes, we want height. So I think same formulas we can use. Let us see. First I will take some examples, then we will discuss this. Now if the number of nodes are given, we have to find out what could be the minimum height, what could be the maximum height for those number of nodes. So here I have already taken some examples. Using 3 nodes, I can generate a binary tree of minimum height 1, 0, 1. And with that same 3 node, I can stretch the height up to maximum 2, 0, 1, 2 for 3 nodes. Next, I have taken an example of 7 nodes. So for 7 nodes, 1, 2, 3, 4, 5, 6, 7, this is the minimum height. Height is 2, that is 0, 1, 2. And these 7 nodes, maximum height is 6. Then for 15 nodes, minimum height is 3, maximum height is 14. Now we want the formula for minimum and maximum. First of all, we will find the formula for maximum. Let us check maximum. Maximum height for 3 nodes, height is 2. For 7 nodes, height is 6. For 15 nodes, height is 14. So there is some pattern. Whatever the nodes are, height is 1 less than that. Nodes are 7, so height is 6. Nodes are 3, so height is 2. So height is 1 less than the number of nodes. So yes, we got the formula for maximum height. So maximum height formula, h is equals to n minus 1. We got the formula. Now what is the minimum height formula now? If I check the minimum height, number of nodes are 3. So minimum height is 1. Number of nodes are 7. So minimum height is 2. Number of nodes are 15, so height is 3. So I don't find any pattern here. So I'll show you something here. See, these are the formulas just now we have found out. If height is given, then minimum nodes and maximum nodes, we have already written the formula. Minimum nodes n is equals to h plus 1, maximum nodes is equals to n is 2 power h plus 1 minus 1. We have seen this formula. Now, we are finding out now if nodes are given, then find out minimum and maximum height if nodes are given. So for that, maximum height we got h is equals to n minus 1. So that's similar to this one. H is equals to n minus 1. H is equals to n. This plus 1 you send it there. So minus 1. So this was the minimum nodes formula. It became maximum height formula. So it means maximum node formula can be converted into minimum height formula. So I don't have to observe from the trees. Let us use this formula and convert it. Okay. So what is the formula? N is equals to 2 power h plus 1 minus 1. So I will find out here. N is equals to 2 power h plus 1 minus 1. This is the formula, right? This is for maximum nodes. So this I can write it as n plus 1 is equals to 2 power h plus 1. That minus 1 I brought it here. Then I will change the side. So 2 power h plus 1 is equals to n plus 1. Now h plus 1 is log base 2 n plus 1. So if you send this base, that side it becomes log. So h plus 1 is equals to log base 2 n plus 1. Finally, this h is equals to log base 2 n plus 1, and this plus 1 if I send it there, minus 1. So I got the formula for h. H is equals to log base 2 n plus 1 minus 1. From where I got this one? From this one. See, from this formula, this was in terms of h to find out n. I converted it in terms of n to find out h. This is the answer for minimum height. Minimum height. So if n nodes are given, the minimum height will be based on this formula. Let us verify this one. See, I am having 15 nodes. What could be the minimum height? We know the answer 3. Let us check it. H is equals to log 15 plus 1 minus 1. So this is log 16 base 2. Log 16 base 2 minus 1. Log 16 is how much? 4. minus 1, this minus 1 as it is, this minus 1, this is 3. Yes, we are getting the answer. So from these formulas, we can derive other formulas, right? So if you know the formula for height, you can get the formula for nodes. So I will write down those formulas. H is equals to n minus 1. H is equals to minimum formula, that is log base 2 n plus 1 minus 1. Maximum formula n minus 1. So we got the formulas. So I will remove this and finally show you two formulas. These formulas, I'll show them here. Finally, from the observation, we got a range of values. See, first formula we saw is this one. Number of nodes in a binary tree. Number of nodes. Minimum h plus 1, maximum 2 power h plus 1 minus 1. This is based on height. If you know the height of a binary tree, then in that binary tree, minimum number of nodes can be these many, maximum number of nodes can be these many. Next, we saw this formula, height of a binary tree. This is very important. Height of a binary tree can range from log n to n, logarithmic to linear. Then this is order of log n, and this is order of n. So minimum is log n, maximum is n. So height of a binary tree can range from log n to n. Remember this one always. So binary tree means log n to n. Whatever the board work I have done, you do it once, then you will always remember these formulas. These formulas are very important. Now we are going to find out relationship between internal nodes and external nodes, that is non-leaf nodes versus leaf nodes. So for finding the relationship, already I have some examples. So let us find out leaf nodes and non-leaf nodes, then we will see if there is any formula in between them, is there any relationship between them. So let us find out. Here, how many nodes are there with degree 2? Number of nodes with a degree 2. This is having 2 children, so degree 2. This is also having 2 children, so degree 2. Any other node? No. So there are 2 nodes with a degree 2. Then how many nodes with a degree 1? This is having just 1 child, degree 1. This is also having just 1 child, degree 1. So there are 2 nodes with a degree 1. Then how many nodes are there with a degree 0? 1, 2, 3. 3 nodes are there with a degree 0. So I have found out all the nodes with a degree 2, degree 1 and degree 0. Right? So I'll do the same thing for other 2 examples also. Then we will see is there any formula. Now in this tree, number of nodes with a degree 2. This is having both the children, degree 2. This is having both the children, degree 2. This is having both the children, degree 2. Any other node? No. So 1, 2, 3. 3 nodes with a degree 2. Then how many nodes are having degree 1? This is having degree 1. This is also having degree 1. This is also having degree 1. So 1, 2, 3. And this is also having degree 1. This is also having degree 1. So total how many? 5 nodes. 5. 1, 2, 3, 4, 5. Then how many nodes with a degree 0? 1, 2, 3, 4. These nodes are not having any children. So degree 0 nodes are 4. See, these are internal nodes and this is external node, right? These are internal and these are external. So these two together, internal means they must have either 2 children or 1 child. No children, 0 children means leaf nodes, right? External nodes. Let us observe here. How many nodes with a degree 2? Only 1. Yes. How many nodes with a degree 1? This is having degree 1, 2, 3, 4. 4 nodes with a degree 1. Then how many nodes with a degree 0? 1 and 2. So 2. I have written the values here. So there are some hints I have given in this values. You find out what is the relationship. 2, 3, 3, 4, 1, 2. So there is a relationship between nodes with a degree 2 and degree 0, but not degree 1, but not degree 1. Degree 2 and degree 0, there is a relationship. So what is the relationship? Number of nodes with a degree 0 are equal to number of nodes with a degree 2 plus 1. Yes, This is always true in binary tree. This formula is always true in binary tree. So that's all about the formulas. The relationship between internal nodes and external nodes we have seen. We will learn about strict binary trees. Strict binary trees are also called as a proper binary tree, or sometimes they are also called as complete binary tree. This type of tree is for analysis. If you have a binary tree and you found that it is a strict, then whatever the analysis we are learning that are suitable for that strict binary tree. So we will be learning height versus nodes that we have already seen in binary tree. So here what are the changes we will look at. Then internal nodes versus external nodes. This also we have done in binary tree. Let us see what is the formula for internal and external nodes in strict binary trees. So let us find out what are strict binary trees. So first of all, let us know what are strict binary trees. A general binary tree means every node can have 0, 1 or 2 children. But in a strict binary tree, a node can have either 0 children or exactly 2 children. A node cannot have 1 child. So strict means it must be strictly binary. There should not be any node with degree 1, that is unary. So here I have some examples. Let us check those examples to understand more clearly about strict binary trees. Let us look at this binary tree. This node is having 2 children. Okay, allowed. This node is having 2 children. Yes. This node is having 2 children. Allowed. What about this node? No children for this one. What about this node? Degree 0, degree 0, degree 0. Yes, perfect. What about this? Degree 2, degree 0, degree 2, degree 0, degree 0. Yes, perfect. What about this one? Degree 2, degree 0, degree 1, degree 1. This is not allowed. So this is not a strict binary tree. What about this one? Degree 2, degree 1. So because of this, there are other also. This one is also there. So because of these nodes, it is not a strict binary tree. This one, for this node, degree is 3. So this is not even a binary tree. Let us look at this one. Degree 1, degree 1. So this is not a strict binary tree. So in this example, these two are strict binary tree and rest of them are not binary trees, and this is not even a binary tree. Let us look at height versus nodes. For that, already I have taken some example. Let us look at the examples. Here I have taken height 2. So in height 2, minimum these many nodes are possible, maximum these, that is 7. And here height is 3, minimum node 7, maximum 15. And height is 4, minimum 9 and maximum are 31. I did not draw the complete tree there. If you observe, the maximum number of nodes are same as a binary tree formula. Maximum number of nodes are same, whether it is just a binary tree or a strict binary tree. Then what is different here? Minimum number of nodes. See, if it is just a binary tree, then these nodes are not required. Minimum 3 nodes are sufficient. But here 5 nodes because it has to be strict. So for being strict, every node must have either 0 or 2 children. So 5 nodes, 7 and 9. So what is the formula? 5, 7, 9, next it may be 11, then 13. So it's going by odd number. So we need the formula for minimum. If height is 2, then 2 plus 2 plus 1. So 2 into 2 plus 1. If height is 3, 2, 2, 2. So 3 times 2, then root 1. So 2 into 3 plus 1. And here height is 4. So this is 2, 2 nodes, 2 nodes, 2 nodes. So 4 times 2 nodes plus 1. So what is the formula now? So now we can frame the formula. Whatever the height is, 2 into height plus 1. Minimum number of nodes are 2 into height plus 1. What is the formula for maximum nodes? 2 power h plus 1 minus 1. We already know that. So let me write on the formula. Here, if height h of a strict binary tree is given, then minimum how many nodes are required? Just now we have found the formula, that is 2 into h plus 1. Then maximum how many nodes are possible? Maximum. This is same formula, 2 power h plus 1 minus 1. These are the formulas if height is given and we have to find nodes. Then what are the formulas if nodes are given and we have to find out minimum and maximum height? So those formulas we can obtain them from here. Already we have learned in binary tree that if you know these two formulas, just convert them, we can know the formulas for height. So let me write on the formula here. Here, if n nodes are given, then what is the minimum height and what is the maximum height? So minimum height we can get it from this maximum formula. This is n equals to so and so in terms of h. We should convert it h equal to whatever the formula is in terms of n. So we have already converted this in the previous video. So this is log n plus 1 base 2 minus 1. Yes, this is log base 2 n plus 1 minus 1. Then what about the maximum height formula? That we can get it from minimum nodes formula. So n equal to 2h plus 1. So write it in terms of n. So h is equals to n minus 1 by 2. N minus 1 by 2. So that's it. These are the formulas. Now here the formula for height is important. So height, if you observe, minimum height is log n base 2. Log n plus 1 base 2 minus 1, and the maximum height is n minus 1 by 2. So if you observe this one, this is logarithmic and this is linear. So height is ranging from log to n. So the height property is similar to binary tree only, that is maximum height can be in terms of n. Now let us look at internal nodes versus external nodes, that is non-leaf nodes versus leaf nodes of a strict binary tree. So for explanation, already I have taken some example strict binary trees. Let us look at them. Say this strict binary tree, how many internal nodes? 1 and 2. 2 internal nodes are there. How many external nodes? 1, 2, 3. These are leaf nodes. In this strict binary tree, number of internal nodes 1, 2, 3. External nodes 1, 2, 3, 4. So 4 leaf nodes are there. And in this one, internal nodes 1, 2, 3, 4, 5. Internal nodes are 5. Then how many external nodes? Leaf nodes 1, 2, 3, 4, 5, 6. 6. So from these examples, we can see that internal nodes are 2 and external are 3. This is 3, so this is 4. And if it is 5, then this is 6. So leaf nodes are 1 greater than non-leaf nodes, or external nodes are 1 greater than internal nodes. So we can come up with the formula E is equals to I plus 1. Yes, this formula is always true in strict binary trees. And in strict binary tree, this formula is more important. That is number of internal nodes plus 1 is equals to number of external nodes. In this topic, we'll learn about what are n-Ary trees and what are strict n-Ary trees. Just like strict binary trees, we can also have strict n-Ary trees. Then height versus nodes of strict n-Ary trees. Then internal nodes versus external nodes. See here one thing you can observe, these are n-Ary trees, but I have given the heading as m-Ary. Reason, n means we are calling them as number of nodes, right? In previous videos, we have called n as nodes. So it may create confusion. So for degree, I gave the name as m-Ary. Let us learn what are n-Ary trees. In this video, we'll learn about n-Ary trees. N-Ary tree. N is the degree of a tree. Degree means every node in a tree can have at most n children, not more than n children. Let us take the examples and study. See here the example is a 3-Ary tree, a tree with a degree 3. So every node can have 0, 1, 2 and 3 children, any of these. So the capacity of each node is maximum 3. It can be from 0 to 3, but not more than 3. So if it is less also, we should accept it. These are my examples. I have drawn them and saying that these are all 3-Ary trees. Alright. So I have declared that these are 3-Ary. So let us check really they are 3-Ary or not. First one, degree 3, degree 2, degree 3, degree 0, 0. Yes, no node is having degree more than 3. Yes, it's perfect. It's a 3-Ary tree. What about this? Degree 2, degree 3, degree 1, degree 0, degree zeros. Yes, no node is having degree more than 3. Yes, it is 3-Ary tree. Degree 2, degree 0, 0, 0. No node is having degree more than 3. Yes, it's a 3-ary tree. It's looking like a binary tree. Is it not a binary tree? Yes, it is also a binary tree. But I said that every node have the capacity to have 3 children. If they have less, then no problem. When I said that this is 3-ary, so it is 3-ary. So who will decide the degree of a tree? By looking at a tree, we cannot decide the degree, right? Degree of a tree is pre-decided. So that's what I am drawing the trees. I said that these are 3-ary. So based on the condition, yes, this is 3-ary. That's it. So from the tree, you cannot judge its degree. Now I have one more example. Let us look at this. 4-ary. So every node can have 0, 1, 2, 3, 4 children, not more than 4 children, right? Now this is a tree. 2 children, 4 children, 2 children. Yes, perfect. 2 children, 3 children. Perfect. See, this also is looking like a 3-ary. But as I said that every node is having capacity of 4 and I am drawing it as a 4-ary as per the conditions. Yes, it is 4-ary. What about this one? 1, 2, 3, 4, 5. No, nodes cannot have degree more than 4. This is not a 4-ary tree. So what does it mean? I'll explain you a little bit. See, if you have the idea, I'm assuming that you already know this type of thing. So node structure, suppose the value in here is 10. Now this is a node. How many children it can have? 4 children it can have. So what is the degree of a node? It is having 4 children. So all the nodes in a degree 4 will have the capacity of having 4 children. Suppose this node is not having all 4. This is null. Then what is the degree of a node? Just a 3. But what is the capacity? 4. If the degree is 3, we will not say this node is belonging to 3-ary tree. No. See the capacity. That is null. Then if suppose this node is also not there, then it's binary. No. Based on the node, we cannot say. See the capacity. This node belongs to 4-ary tree. Right? No doubt a node is not having all 4 children. That's why I said, if I am making a tree, then I will decide the degree of a tree. Right? Next, we'll be looking at strict n-Ary trees. Now, strict m-Ary tree. A strict m-Ary tree is one in which every node can have either 0 children or exactly m children. For example, I have a strict 3-Ary tree here. These are some example trees. Let us check which of these are strict 3-Ary trees. Strict 3-Ary means every node can have either 0 children or exactly 3 children. Not less, not more. Let us look at the first example. Degree of this is 3. Okay, perfect. Degree of this is 3. Perfect. So these two are over. Degree of this is 0, 0, 0. Degree 0, degree 0. Yes, perfect. Degree is 0 or 3, right? So only 0 or 3. Only 2 degrees are allowed. Degree 3, degree 3, degree 3, degree 0, 0. All these are 0. Yes, this is also strict 3-Ary tree. Degree 3, perfect. Degree 0, 0. Degree 2, wrong. This is not a strict binary tree. One of the node is having degree 2, so it's not a strict 3-Ary tree. Degree 3, degree 2, no, wrong. That's enough. One node is violating that condition, then I don't have to check the rest of the nodes. So this is not a strict 3-Ary tree. So these are the two examples of strict 3-Ary tree. We will do analysis of height versus nodes. This type of analysis we have already done on binary trees. So I will not do much explanation here. Directly I will try to write on the formula. We have to get the formula for height versus nodes of strict m-Ary trees, right? But as an example, I have taken a strict 3-Ary tree. So from these example trees, we will get the formula for m-Ary tree. Let us look at this. See, height of a tree is given as 2, and these are minimum number of nodes it can have. These are maximum nodes it can have. And the height is here 3. So these are the minimum nodes it can have. These are the maximum nodes it can have, right? These are also nodes, okay? So I need the formula. If height is given, minimum how many nodes, maximum how many nodes. So let us write the formula. Let us observe and write the formula. See, height is 2 means how many nodes are there? 3 plus 3 plus 1. So 3 plus 3 plus 1. It's nothing but 2 into 3 plus 1, right? Number of nodes. Then here when it is minimum 3 plus 3 plus 3. So this is 3 into 3 plus 1. Number of nodes are there. So it means if height is given, then minimum nodes. How many minimum nodes are there? See, this 3 is a degree and 2 is height. 3 is a degree and 3 is height here. So 3 into h plus 1. So whatever the height is into 3 plus 1. But actually this 3 is degree of a tree. So I should call it as m. So I will rewrite the formula. This is m into h plus 1. Yes, this is the formula. So in a strict n-Ary tree, minimum number of nodes will be n equal to mh plus 1. Then the maximum nodes how many? Let us observe. 1, then 3, then 9. What about this? 1, then 3, then 9, then 27. If I write them, this is 1 and this is 3 and this is 3 square. This is 3 cube. So this is 1 plus 3 square plus 3 cube. So these are the terms of GP series. Yes. But what is this 3? 3 is degree m. So I will rewrite it like this. 1 plus m square plus m cube plus goes on up to whatever the height is. So this GP series, if I add, then if you remember the formula for GP series, I'll write on the formula. A r power k plus 1 minus 1 by r minus 1 is the formula. So for this series, what is the formula? A is what here? A is 1. Okay, don't write it. Then r, common ratio is what? M. Power, k is what? H plus 1 minus 1. So m power h plus 1 minus 1 divided by m minus 1. This is m minus 1. Yes, this is the formula. See, once again I'll tell you, maximum how many nodes possible in a strict 3-ary tree. The total number of nodes are forming a GP series formula. This is for degree 3. I convert it into degree m. Then this is the formula for some of the terms of GP series. This is the GP series. Then using the formula, I have added this one. I got a formula for this one. So m power h plus 1 minus 1 by m minus 1. So the maximum nodes are n equal to m power h plus 1 minus 1 by m minus 1. So that's all, we got the formulas. If you already know the height, then the minimum how many nodes, maximum how many nodes. Now the other formula we have to write on. If we know the number of nodes, then minimum height and maximum height. This was minimum nodes, maximum nodes. So I will write on for height. So if n nodes are given, then what is minimum height and maximum height? These formulas I can get them from here. Like the minimum nodes can give me maximum height formula. See, here it is n equal to mh plus 1. What is h? That 1 if you send here, n minus 1. Then m comes in denominator. So this h is equals to n minus 1 by m. Yes, n minus 1 by m. Then what about this maximum nodes formula gives minimum height? So this is having power. So definitely this will be in terms of log. So you can convert this one, do paperwork and convert this. I will directly write on the formula there. See, this is the formula, log base m, n into m minus 1 plus 1, then entire result minus 1. So if you convert this, you get that formula. So these formulas are more helpful when you want to know maximum how many nodes are possible and what is the minimum height possible. So minimum height, you can see that it is logarithmic and maximum height is in terms of n. So this is logarithmic and this is linear. The purpose of all these analysis is to know the space and the time taken by trees when we really use them. When we use the trees, that time we will use these formulas also, right? That time I will not discuss. I will be discussing how to use them rather than discussing the formulas. So we are first analyzing and keeping the formulas ready, then we will use them afterwards. Next, one more formula is remaining, that is number of internal nodes versus external nodes. So I'll take the same example trees, I will remove this and let us find out number of internal nodes and external nodes. So from these example trees, let us find out internal nodes and external nodes for a strict 3-ary tree. Then we will prepare the formula for any m-ary tree. Let us observe. How many internal nodes are there? 1, 2. Internal nodes are 2. External nodes 1, 2, 3, 4, 5. Internal nodes 1, 2, 3, 4. 4. External nodes 1, 2, 3, 4, 5, 6, 7, 8, 9. Internal nodes 1, 2, 3. External nodes 3, 4, 5, 6, 7. Then internal nodes here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. External nodes, these are 3 power 3, that is 27. So can you find any pattern or the relationship between the values? Let me check. 2 and 5. 2 into 2 plus 1. Okay, 2 into 2 plus 1 gives me 5. Then 4 into 2 plus 1. So I will write 2 into 4 plus 1. Yes, that is 9. Then what about this? 2, 3, 6 plus 1, 7. Yes, 2 into 3 plus 1 gives 7. What is this? 2 into 13, 26 plus 1. Yes, 2 into 13, that is 26 plus 1 gives 27. So it means external nodes are equal to 2 into number of internal nodes plus 1 for a strict 3-ary tree. Then for strict m-ary tree, E is equals to, see this was 3, so I got 2. So for m, it will be m minus 1 into I plus 1. Yes, this formula is for internal nodes versus external nodes. This is for any strict n-ary tree. Now the topic is representation of binary tree. There are two representations. One is array representation and second one is linked representation. Let us start with array representation. Let us look at array representation of binary tree. I have an example binary tree here. Labels are alphabets, so that's easy for you to understand. Also I have an array, and one thing is array index is starting from 1 onwards. But in C++, array indices start from 0 onwards. So for storing in C++, we can ignore the index 0. If at all you want to use that also, we will see it afterwards. So right now, array indexes start from 1 onwards. Now how to store this binary tree? For storing a binary tree, I have to store two things. First one is all the elements, that is A to G, and the relationship between those elements. Like A is a parent of B and C, or B is a left child of A, C is a right child of A. Likewise, B and C are also having their children. So if we are maintaining parent and child relationship, then we can produce a tree back again. So just storing the elements will not be sufficient. We should also preserve their relationship. How I can do this? Elements, I can store them in these spaces. Yes, it's okay. But how to maintain the relationship? Maybe this indices may help me. The index of each location can help me to preserve the relationship. Yes, I will use that. How? I will show you. So first of all, I will fill the elements. Then I will show you how they are maintaining the relationship. I will store these elements level by level. So the first level element is A. The next level, second level, B and C. So okay, I will store B and C. Then third level, D, E, F, G. So D, E, F, G. I have stored all the elements. Now I have to see whether the relationships are preserved or not. Let us observe the indices. Here I will prepare the table of indices. With that you can understand. See, the first element is A. A. What is the index of this element? 1. Then who is the left child of A? B. Where is B? At 2. Okay, it is at 2. Then who is the right child of A? C. So what is the index of C? 3. So right child index is 3. Then next I'll take element B. What is the index of B? 2. Left and right child, D, E. Where is D? 4. And right child, E, is at 5. Then let us take C. C. It is at index 3 here. The index of this element. Then who is the left child of C? F. Where it is? 6. Then who is the right child of C? G. Where it is? At 7. So I think this is sufficient to understand how the relationships are maintained with the help of indices. See, when an element is at index 1, then its left child is at 2 and right child is at 3. If the element is at index 2, then left child is at 4 and right child 5. So 2 into 2, right, 4. So 2 into 2 plus 1, 5. 2 threes, 6. 2 threes plus 1, 7. So yes, this is the formula maintained. If any element is at index I, then its left child is at index 2i and right child is at index 2i plus 1. So elements are stored based on this formula, right? If any element is at index I, then its left child is at index 2i. Then right child is at index 2i plus 1. So these are the formulas used. Now one more thing. If I take any element, then where is its parent? Like for example, F. Who is the parent of F? C. So F is at 6, C is at 3. So when this left child we are getting it by multiplying it by 2. So parent we will get it by dividing it by 2. So the parent of any node will be at I by 2. When you divide any number by 2, you may get a decimal result. So shall we take it or not? Let us check. G is a child of C. G is at 7. Where is its parent? At 3. So this is 7 by 2 is a 3.5. So we should take the floor value, that is 3. So yes, this is floor value. So for any node, these formulas will help us to obtain its left child, right child or parent. Now, when I was filling these elements, I did not follow this formula. I just filled them level by level. And automatically those formulas are applied. Yes. So for filling it, either you follow the formula or fill them level by level. Automatically this formula will be followed. So that's it. This is the array representation of binary tree. Now I will take few more special cases. Now let us look at linked representation of binary tree. So the same example binary tree I have taken. Now linked representation means we will be using nodes, like nodes of linked list. So yes, we will use a node. Node structure will be containing data and 2 pointers, left child and right child. So this node structure is same as the node of doubly linked list. In doubly linked list we'll have previous pointer and next pointer. Here we are taking left child and right child. This node can be defined using self-referential structure node having 2 pointers. This is a self-referential pointer, L child and right child, and in between data is also there. So we say linked representation, we don't say linked list representation. List means it is linear, but a tree is non-linear data structure. So now next let us see how we can utilize these nodes and represent this one. So for every node in a binary tree, we will create this structure node. So I have kept the structure ready for this tree. So this is a node for A and this is B, C, D, E, F and G. This A is having 2 children, B and C. B is having 2 children and C is also having 2 children. What about D? There are no children for D. There are no children for E. Okay, so these are all null. So if there is no child, I have made it as null. So this structure will be dynamically creating, so it will be definitely created in heap. Whereas array representation, array can be created in a stack also or heap also. So it can be static as well as dynamic. But this structure is definitely dynamic, so it is created in heap. Now let us study something about this one. There are n nodes. N nodes are 7 nodes, right? Because these are 7 nodes in this graphical tree. So here also in a linked representation we have 7 nodes. Then How many null pointers are there? 1, 2, 3, 4, 5, 6, 7, 8. When there are 7 nodes, there are 8 null pointers. N plus 1 null. N plus 1 null pointers. Always for any shaped binary tree, you represent it using linked representation. Then, if there are n nodes, then definitely there will be n plus 1 null pointers. So if you remember this formula, that is if n nodes then n plus 1 null pointer, this is similar to E is equals to I plus 1. This we have studied in strict binary tree. Strict binary tree, we studied that number of external nodes will be internal nodes plus 1. So similar formula. If n nodes, then n plus 1 null pointers. I'll remove one node and show you. If I am removing this node, then this should be null. How many nodes are there? 1, 2, 3, 4, 5, 6. How many null pointers are there? 1, 2, 3, 4, 5, 6, 7. Yes, 7 null pointers are there. So that's all about linked representation. Mostly we will be using this representation for writing programs or algorithms over a binary tree. In this video, we'll learn about full binary tree and complete binary tree and also see the difference between them. The concept is very simple. So already I have example trees. Let us look at them. This is a full binary tree, example of full binary tree. What is full binary tree? A binary tree of height h having maximum number of nodes is a full binary tree. What is the height of this binary tree? Height, if I take, this is 0 and here 1 and 2. So 0, 1, 2. Height is 2. So how many nodes are there? Maximum nodes. So maximum node means can I add one extra node and still the height be 2? No. If I add any node anywhere, the height will increase. So up to height 2, it is having full nodes, that is maximum nodes. So a tree of height h can have how many nodes? 2 power h plus 1 minus 1 nodes. So what is h here? 2. So if I write 2 here, this is 2 plus 1 minus 1. This is 8 minus 1, that is 7. 1, 2, 3, 4, 5, 6, 7. Yes, 7 nodes. If you remember the formula, a tree of height h can have maximum 2 power h plus 1 minus 1 number of nodes. So yes, this is having maximum nodes. So it's a full binary tree. So that's all. This is the definition of full binary tree. I will represent that in an array. A, B, C, D, E, F, G. I have filled them level by level. So it is stored in an array. Now we have to understand what is complete binary tree. Now this concept is important. Complete binary tree. Listen carefully. For explaining complete binary tree, I have taken 2 examples. So first one, this one is complete. This is not complete. How? Let us see. I will represent that in an array. So first one is A. Then B, C. Then next level D, E, F blank. So okay, D, E, F. F is the last element. That's all. The size of the tree is 1 to 6 only, right? 1 to 6 only. Now from first element to last element, are there any blank spaces in between? No, there are no blank spaces. So this is a complete binary tree. Now I'll define it. If a binary tree is represented in an array, then there should not be any blank spaces in between the elements. If there are blank spaces, it's not a complete binary tree. There are no blank spaces, it is a complete binary tree. Now I have one more example. Let us store this one. Then we will see whether it is complete or not. Let us store level by level. A, B, C. Yes, 2 nodes. B, C. D. Then here there should be an element. Here there should be an element. These nodes are missing. So D blank blank E. So D blank blank E. So I got 2 blank spaces. First element is A, last element is E. In between those 2 elements, 2 blank spaces. This is not a complete binary tree. This is a complete binary tree. Now I will give a book definition for complete binary tree. A complete binary tree of height h. Here height is 0, 1, 2. A complete binary tree of height h will be a full binary tree up to h minus 1 height. So h minus 1 height, if you look at this, hide these, then just look at these, it's a full binary tree. Yes. And in the last level, the elements will be filled from left to right without skipping any elements. Left child, then right child, then left child, that's all. Finish. No problem. Finish. As many elements we had, we have filled them from left to right without skipping. Without skipping means I am not writing this right child but taking left and right child here. Suppose this is E and this is F. Then this is missing. This is missing. So it's not a complete binary tree. So last level, the elements must be filled from left to right. Let us look at this. Up to this height it is full, but last level the elements are not filled from left to right. Left, then next one is this one. Here it is missing. So missing means it's not a complete binary tree. So this is the definition of complete binary tree. Why? Why we need complete binary tree? See, we have learned arrays, and also we have used arrays for stack as well as queue. And every time I was telling you that we should not have blank spaces in between the elements. If any element is deleted, we should shift the elements and occupy that place. Then how we can have blank spaces in an array? So if a tree is such that you are forced to have blank spaces, then it is not suitable for array. So we say it's not a complete binary tree. We say complete if it is suitable for array. Now coming back to this. This is a full binary tree, right? This is a full binary tree. Is it complete? Yes, it's a complete binary tree. There are no blank spaces in between the element. So a full binary tree is always a complete binary tree. This is a well-known statement. But a complete binary tree, I will change this. This was E and this was F. Okay, back to that. But a complete binary tree need not be a full binary tree. Right? If it is complete, not necessary it is full. But if it is full means definitely it is complete. So that's all the differences between full and complete binary tree. We have learned about strict binary tree and complete binary tree. Let us compare them. See, a strict binary tree is also called as a proper binary tree. The definition is every node can have either 0 degree or degree 2, means no children or 2 children. Then we learn complete binary tree. Complete binary tree means when it is represented in an array, there should not be any blank spaces in between the elements. Or other definition, if the height is h, then up to height h minus 1, it is full. Last level, the elements are filled from left to right. So strict is different, complete is different. But some authors at some places you may find complete binary tree definition as a strict binary tree. So it means strict binary tree is also called as complete. Then what do you call to that one? That is sometimes called as almost complete. So if this is called as complete, then this is called as almost complete. If you call this as strict, then you can call that one as complete. So there is no fixed name for this one. So as per your requirement, you can call it with any name. Now let us compare their examples. See, this is an example of a strict binary tree. So strict binary tree means every node can have either degree 2 or 0. Degree 2, these are 0. Yes, perfect. But this tree, when I store in an array, there are blank spaces. So this binary tree is strict, but it is not complete. It is strict, but not complete. I prefer calling these names, right? Strict and complete. So this is strict, but not complete. Complete means there are blank spaces here. That's why it's not complete. Then what about this? This is having degree 2. This is having degree 2, degree 0, degree 0, degree 0. So this is strict. Yes, this is strict. What about complete? First element to last element, there are no blank spaces in between the elements. Here we have spaces, you see, 2 spaces. There are no blank spaces. So this is also complete. So this is strict also, complete also. So from the examples you can understand. I will draw a few more trees, then we will see whether they are strict or complete or not. We will compare them. Tell me, is it strict or complete or nothing? What it is? This is not strict because this is having degree 1. So this is not strict. But whether it is complete, let us store it in an array and see. A, then BC. Then from left to right, right? So these are not there. So only D is there. Yes. So from first element to last element, there is no gap in between the elements. So this is complete, but not strict. So strict, this is not strict, but it is complete. See, this was strict, but not complete. This was both strict as well as complete. That is complete, but not strict. Then one more I will take. This one. Is it strict? This node is having just one child, so it is not strict. Let us see whether it is complete or not. So I will store them in an array. So first is A, then left, right, B, C. Then from here, these elements are missing, blank, blank, then D. And this is also missing. Okay, that is outside the, that is after D, we don't need it. So you can see that there are blank spaces here. So it's neither strict nor complete. Right? So I have all type of examples, only strict, both, only complete, nothing. So I have compared both of them. Now choice is yours, whatever the name you want, you can call them with that name. And complete binary tree is more useful. We will be using it afterwards. In one of the topic, we'll be using complete binary tree. This one we'll be using. This is very important because there are no blank spaces, means we can use this in an array. The topic is tree traversals. Traversing means visiting all the elements or visiting all the nodes. If a data structure is linear, then we can traverse in two methods. First to last, that is forward, or last to first, backward. But when it is non-linear, then what are the possibilities? So for binary trees, these are possible traversals. Pre-order, in-order, post-order, and level order. So let us learn about these traversals. So first I will read out their definitions. Pre-order means visiting a node, first visiting any node, then performing pre-order on its left subtree and performing pre-order on its right subtree. Usually we read it like this. Root, we say root, left, right. But this is the perfect definition of pre-order. Then in-order traversal, first perform in-order traversal on left subtree, then visit a node, then perform in-order traversal on right subtree. Then post-order traversal, perform post-order on left subtree, right subtree, then visit a node. And last one, level order means visit all the nodes level by level. So here I have example trees of height 1, that is small trees. Let us see what is the result of these traversals. So first tree I will take pre-order of this one. I'll write in short pre. Pre-order means first root or a node A, then go on its left, then go on its right. So A, B, C is pre-order. Then what is in order? First left, then that node A, then its right. So B, A, C is in order. Then post order. First left, B, then right, C, then A. This is post order. And the level order for this one will be A, next level B, C. So A, B, C. First level A, the next level B, C. Then here I have taken only two nodes, that is a root node and its left child, only two nodes. Let us see what will be the result of these traversals. First pre-order. First root A, then left B. There is no right, leave it. Then in order. First left, then root. There is no right, leave it. Post order. First left, then right, there is no right, then take root. Then level order. First level A, the next level only B is there, B. So if you observe in this in order and post order are same for that particular tree because it is not having right child, so post and in order are same. Now one more tree I have, let us write the pre-order. First root, then left, there is no left, then right, okay, take it right. Then in order. First left, there is no left, then take root, then right, B. Here in this tree, pre-order and in order are same. Then post order. First left, there is no left. Then go to right. Okay, take right. Then root A. Then level order. Level by level. First A. Second level, there is no element here. Only this element is there. So take B. So for these small examples, I have shown you how these traversals are. So actually we have understood what is the meaning of these traversals. Now if the tree is larger, if it is bigger, then how it is performed? Let us look at. Now for a bigger problem, a bigger tree, let us find the traversal. So the traversals that I am going to show you are based on the definitions we saw. Then there is a shortcut or easy method for finding the traversal. Just by looking at a tree, you can tell the traversal. That I will show you how to do that. But now let us follow the definition. As per the definition, I will show you how to find the traversal. This tree is bigger. We have just now seen a smaller size tree and directly we were able to find the traversals. So just 3 nodes were there, height was 2, but the height is more. So break this tree into smaller size trees. Means it's a large problem. So break the problem into small size problems. How we can do that? Let us see. See, this is root. Yes, root of a tree. Then this is the main node. Then this is its left child and right child. Left child is not just one node. It is having its children also. So make it as a separate subtree. Then right child, it's not just a child, it is having its own children also. It is having its own family. So okay, separate this family. So this is a subtree and this is also subtree and this is the root of main tree. Now from main, if you see, that is root, left is a single block, right is a single block. Then inside that, if you see, again it's a tree. So this is based on the definition I am doing. Again I am telling you. Now let us find out preorder. First root A. Then left child. This is a tree. Okay, put the bracket. Later we will see what to do. Then right child. This is not just one child. It's a tree, subtree. So okay, put the bracket. We'll see afterwards. So this preorder is completed based on this tree. It is completed. And those blanks are there, we have to fill them. Now for this bracket, this is the child, right? What is the preorder for this one? 3 nodes. Directly we know the answer. B, D, E. Root, left, right. So B, D, E. Then what about this one? This belongs to this. So this is a tree with just 3 nodes. So we directly know the answer. Root, left, right. C, F, G. That's it. This is the preorder. Let me open the brackets and write them. A, B, D, E, C, F, G. This is the preorder. So based on the definition, I have done it. So this is the preorder. Now next, I'll show you in order. In order of a tree. For this root or for this node, first left. This is not just one node. It's a subtree. Okay, put the brackets. We will see it afterwards. Now parent. Now parent, that is root, take this node. Then right child, it's not a child, it's a subtree. Okay, put the brackets, we will see it afterwards. So left, root, right, left, root, right. This is over. Next, fill this bracket, in order traversal of this one. So there are only 3 nodes, we know the in order traversal, that is a D, B, A, left, root, right, D, B, E. Then in order traversal of this part, that is F, C, G. F, C, G. I'll open the brackets and write it. It is a D, B, E, A, F, C, G. This is the in order. Let me finish post order. Post order says first left. This is not just one node. Then right. This is not just one node. Then root. Okay, take A. Then what about this left? There are 3 nodes, perform post order, D, E, B. So D, E, B. This is the right child, perform post order, only 3 nodes are there. So F, G, C, F, G, C. Open the brackets, D, E, B, F, G, C, A. The last one, level by level, first A, then B, C, then D, E, F, G. That's all. So here I write the level order. Level order is A, B, C, D, E, F, G. Yes, A, B, C, D, E, F, G. So these traversals, we have seen them based on the definition of a traversal. So this is the perfect way to understand them. But if a tree is given and you have to find out what is the traversal, if you want to find the result using pen and paper, this is not an easy way to do. Then there are some simple and easy methods available. We'll look at those methods. So now we will learn how we can directly tell the traversal of a tree. Now let us look at an easy method for finding the traversals of a binary tree. There are more than one easy methods are there. So I will show you with first method. So I am going to show for all three traversals. So I have taken same tree 3 times. Let us find preorder upon this tree. Preorder. For finding a preorder, draw a line at the bottom of a tree. Then from every node, from the left hand side of a node. See, this is the left hand side, this is bottom or the middle, and this is the right hand side. So from left hand side, stretch a line and connect to this bottom line. From every node you do that. And these lines should not overlap or intersect. Need not be a straight line. Just you connect them. That's enough. Connect it like this. Connect it. Connect it. All nodes are connected from left hand side to this bottom line. Now scan this line from left to right and see which nodes are connecting. This first node is A. Okay. The next is B. This line belongs to B. Okay. B. Then D. Then this belongs to E. This belongs to C. This belongs to F. This belongs to G. So scan from left to right and take all the elements. This is the preorder of a tree. So simple. Now let us look at in order upon this tree. In order. Draw a line at the bottom. Now from the middle or the bottom of a node, connect a line to this one. Connect a line from here. Middle, that is in between left and right child, right? So there are no left, right, okay? Draw a line, draw a line, draw a line. Scan this line and take the elements whichever are connecting from left to right. So first is D, then B, E, A, F, C, G. This is in order. Then post order. I guess you have understood what you have to do. Yes, connect lines from right hand side of a node. So from right hand side of a node, then this right hand side, then this right side of a node. And scan through this line and take the nodes which are connecting from left to right. D, E, next this is B, F, G, C, A, C, A. This is post order. For any tree you can do this and you can easily find the traversal. Next I will show you one more method, simple method for finding traversals. Now second easy method for finding traversal of tree. So I have same trees for 3 different traversal. Let us find out preorder. Preorder. First, on every node, draw a line on the left hand side. Put a mark on the left hand side for every node. Now next what? Start from the top, root, and go along the boundaries of a tree. This mark we came across, A. Then go along the boundary, right? Don't cross over. This one, B. B's mark we got. D's mark we got. Then get inside, go along the boundary, right? Get into the gulf and come out. So E. Then go inside along the boundary. C. And F. G. Finished. So we started in this direction, gone around the boundaries, then we have reached till root back again. So these are the elements we came across. We came across the left hand side marks of these elements. So this is preorder. Then how about in order? For finding in order, Draw a mark at the bottom of each node. Bottom or the middle, right? In between left and right child. See, this is in between left and right child. Now do the same thing, trace along the boundaries of a tree, start from here, right? Go along, we did not came across any mark. Yes, this is the first mark. So take D, then get inside, yeah, B, then E, A, then along the boundary F, C, G, and this is in order. Now next, post order. Upon this tree I will do post order traversal. Now put a mark on the right hand side of each node, right? Right hand side of each node. Now do the same thing, trace along the boundary. First one, D. So the post order, first one we came across is D. Okay, go inside and come out. Then E, E, B, then F, G, C, then A. That's all. This is the post order. So this is one of the easy method. Now final method I will show you where you don't have to do all these things. Directly you can tell the answer. Now the third method for finding traversals without doing any extra work, directly you can tell the answer. So the easiest method I am showing you, and you can try this method on all these trees. I'll be showing it on one or two examples. So this is the regular tree that I am taking in every example. So I will find out traversals on this tree. So first, pre-order traversal. Pre-order. So start from root and take your finger around this tree, right? Move your finger around the tree. So first node that we came across is A. See, this is completely visible for this finger. Finger direction is this, right? So this is completely visible. Next one is B. Take it. Then D. That get inside, and now E. We are able to point on E. Yes, E. Then get inside C. Then F. Then G. This is pre-order. So move your finger like this in this direction. A, B, D, E, C, F, G. This is pre-order. Then what about in order? Put your finger here. So actually you have to take the bottom, right? Or middle. So node is nothing, no node is visible. Okay, move around, move around. Yeah, the complete node is in the focus and we are at the bottom of this node. So this is D. Then the B, E, A, F, C, G, over. So I'll do it once again. D, B, E, A, F, C, G. Then post order. From this side, put your finger like this. There is no node visible. Okay, move along the boundary, move along the boundary. Yes. D, first one we came across is D. I will write them afterwards. Then come along the boundary. Yes. E, D, E. Then the B. I'll stop here and write down D, E, B I got. D, E and B. Continue. Move along the boundaries. Yeah, the complete node is in focus now. F, G, C, A, F, G, C, A. This is the post order. So we got all the traversal. So it's easy, just by looking at a tree you can tell the answer. You don't have to draw or mark anything on a tree, right? Now one important observation I will show you here. The first element of pre-order and the last element of post-order will always be same. Because first we visit root and here at last we visit root. Now let me do it upon one of the tree. I'll take this one and let us find pre-order, in-order and post-order. So I will not write down, just I will read out. Pre-order A, B, C, D, E, F. Then in-order A, C, B, E, F, D. Then post-order C, F, E, D, B, A. So this is how you can find the traversals for these also. This is a student exercise. You can find out the traversals. So that's all with the traversal. Just using pen and paper we have done it. Next we'll be writing the programs for displaying traversals of a tree. In this video we will learn how to generate a binary tree using linked representation. We have seen two representation, array and linked representation. So I'll be showing it for linked representation. So for generating a binary tree, we can start generating nodes from a root node. First we can create root node. Then we can create left child and right child. But when we are creating a left child and right child, we should know whether the left child and right child are there or not. Like this is a full binary tree or complete binary tree. In this, every node is having both left and right child also. But here, some nodes are not having left child, some are not having right child. So first of all, we should know whether a child is there or not there. If it is there, then we can create and attach it. So this is the main thing that we have to take care. So this is the main thing that we have to take care. We have to check if the child node is there, then we will create it. Then one more thing. We will generate it level by level. So first we will create root, then we will create the nodes of first, second level, then third level, then fourth level, so on. So that same procedure we can use it for a full binary tree also, that we can ask a child is there or not. But here we need not ask. So I will show you the procedure how to generate this tree in a linked representation. So for generating a tree using linked representation, we need a queue data structure. So I'm just drawing an array to show that it's a queue. I will take a queue. So this queue will have front pointer, rear pointer, all the mechanism you know already. So I don't have to explain you its mechanism. Just we will insert and delete the element from the queue. Now let us start the procedure. The very first step is create root node. So create one node and make root point on that node and insert the value, then make this as null. So assume that this is the only node now. This is the first node and this is the only node. Suppose the address of this node is 200. So that address, insert it in the queue. So we need addresses. We don't want value 5. We want address of a node. Insert it here. So this is the initial work that we have to do. So once again I repeat, take a queue, create root node, insert the address of root node in the queue. Now we are ready for repeating procedure. So now the steps are repeating steps. So if you look at one step, one or two steps, you can understand rest. Let us see what we have to do. Take out this address from the queue, so 200, and make some temporary pointer P point on that address. So P is pointing there. Standing on that node, ask whether it is having left child. So yes, as per the tree that we want to create, yes, it is having a left child. Your left child is there. So then create a new node with the help of temporary pointer and insert the value, whatever the value is. Then set these pointers as null. Then as this is having left child, so make this P's left point on this node. And suppose the address of this node is 210. Then this new node, insert it into queue. This has finished one step. So what was the step? I'll just repeat it quickly. We took the pointer from the queue and make P point there and ask whether left child is there or not, and we created it and insert its address. Right child is there or not? Yes, create it and insert its address. Same thing will be repeating again and again. So I'll be creating the entire tree, but before going to the next step, just one thing I want to tell you. Here we have to ask whether left child is there or not. If it is there, then we create. Again ask right child is there or not. If yes, then create. So instead of asking, we can simply take the value of left child and we can put a mark that if the value entered is -1, then child is not there. If it is other than -1, let us say positive, then the value is there. Let us continue and create all the nodes and generate the entire tree. I will do these quickly because already I have explained you. Next step, take out the next address from the queue, that is 210, and make the pointer P point on that. So this is the node. Then being here, ask what is the value of the left side. Left side is -1. So it is -1, don't create anything. Then take the value of right side. The value is 9. So create a new node with the help of temporary pointer T. Then enter the value, make this as null. P is right on this one. Suppose the address of this node is 250. Insert 250 into the queue. So we have finished with left and right. Now take out the next address from the queue, that is 230, and make P point on that node. And ask the left side value. Left side value is a 3. So okay, create a new node with the help of temporary pointer T. Insert the value, make this as null. Then P's left should point on this one. Suppose the address of this one is 300, then insert the address into the queue. Then ask the right child is -1. So if the value is -1, don't create anything. So we have finished with left child as well as right child. Then next step, take out the address from the queue 250 and make P point on that one. So this is 250. Ask the left value, it's there. So that is 4. So create a new node with the help of temporary pointer T. Insert the value, make this as null, and make P's left point on that one. Suppose the address of this node is 350, so insert 350 into the queue. Then ask the right child value is there, yes it is 2, so it is not -1, so take the value and create a new node with the help of temporary pointer, insert the value and make this as null, P is right on this one. And suppose the address is 370, then insert the address 370 into the queue. Then continue. Take out the address from the queue, that is 300. So make P point on that one. Ask for the left child, it is -1, don't create. Then ask for the right child, -1, don't create because there are no left child and right child for this one. Then take out the next address from the queue, that is 350, and make P point on that one. Ask for the left child, it's not there. Ask for the right child, -1, not there. Then move to next. So take out the address 370 and make P point on that node 370. Ask for the left child, -1, it's not there. Ask for the right child, -1, it's not there. Then take out the address from queue. There is nothing in the queue. Queue became empty. So stop. So end of the procedure. And we have generated a tree in heap. And this is the root which is holding the entire tree. So we have learned the procedure how to generate a tree with the help of queue. Now next we have to write a function for generating a tree. So I will show you the program code for generating this tree with the help of queue. So procedure already we have seen for creating a tree. So now I will write on a function. I have written a function here, create. I have taken required pointers like P and T are the pointers that we require. And root pointer, assume that it is global. Then I have declared a queue also. Queue data structure. So we have already learned about queue data structure. So that queue, and it must be initialized. So I am not writing the code for initializing that queue. So assume that it is initialized. Now one more thing, we don't know how many nodes will be there. So we can't determine the size of this queue. So instead of taking an queue using array, we can go for queue using linked list. Now let me start writing the code. As I have already explained you, the very first thing we should do is create a root. So I will write on the code here for creating root. So printf enter root value. Then scanf the value of root in variable x. So I am reading the value. Now next create a node using pointer root and fill this value and make these as null. So I am creating a root node using malloc function and filling the data in that node and making left and right child of that root as null. So I wrote 0 here for null. Then I should insert this address of this root node in queue. So here nq root, this is inserted in queue. As I explained that initially this address 200 we inserted here. Now the repeating procedure I have to write on, that has to be written inside loop. So I can use while loop. How long that loop should continue? Until queue is not empty. If it is empty, it should stop. So I will write down loop here, while not is empty q. So as long as q is not empty, continue. When it is empty, then stop. Then all the steps I have to write down inside this one. So what is the first step? Take out the address from q and take it in a pointer p, that initially we did it like this, right? So p assign dq. So p assign dq from q. So take out a value from q and take it in pointer p. So p is pointing there. Now being there, we should ask the value of left child. If it is not -1, create it. Then ask the right child. If it is not -1, create it. Those steps I have to write down. So I will write down the steps for left child. Printf enter left child. Scanf take the value in variable x. Here I am checking if x is not equal to -1. If it is not -1, then we will create a node with the help of temporary pointer and enter the data and make this as null and make p's left point on that one and also insert the address into the queue. All these steps I have to do. So I will write down these steps. So here, create a new node with the help of temporary pointer, set the data in that node, set the data in the node, and set left child and right child as 0, set left child and right child as null, then also makes p's left as a t, p's left as t, then enter the address of this new node in queue. So insert the address of that new node in queue. So enqueue that t. This all will do for left child. See from here, all these steps are for just left child. Then same steps I should repeat for right child also. Printf enter right child, take the value. If it is not equal to -1, then create a node and this line will change. Instead of p's l child, I should write p's r child. All the steps are same. All the steps are same. So there is no space, I cannot continue. So I should write down all these things once again for the right child also. Then close while loop and close that function. So the steps will repeat here. I should repeat those steps. The steps that are inside this block, all these steps should be repeated again for the right child also. Now while writing the program, I will complete the code and I will show its execution. So that's all. This is the procedure for generating a tree with the help of a queue. In this video, we look at a program for binary tree. We will create a binary tree and also we will see traversals on binary tree. So for creating a binary tree, we need queue data structure where we will be storing the addresses of the nodes. So already we have written a C language program for queue using array. So I will use that same code in my new project. So I will copy this. There's a structure for queue and create function is there, enqueue and dequeue is also there. So I will take all these and display. I don't need display function. Okay, this is enough. I will copy this one. Then I'll start a new project for trees. New project. I'll give the name as a tree and it's a C language project. So yes, create it. Yeah, project is created. Now here I will add a header file where I will write down the functions that are required for queue. So I will say new and file and let it be a header file. Yes, it's a header file and the header file name I will call it as queue. So queue.h is created and inside this I will paste everything. So I have create function and queue and dequeue functions. These functions are for circular queue so that I can use that array circularly. Then here I need more functions, so I will write on them. That is empty function I will write on. It should take a queue as a parameter, that is struct queue and this is queue and it's called by value. It should check if front is equals to rear. So queue dot front, if it is equal to queue dot rear, then it should return whatever the result of this equality operator, it should return. If it is true, it will return true, otherwise it will return false. So this is a queue available. Now one important thing is this queue is going to store addresses of tree nodes, so not integer type data. So here itself I will define a structure for node. This is a tree node, so I can say node or tree node, anything. The members of this one is struct node, that is L child, and integer data, and struct node R child. This is a structure for a node. I have to modify this queue so that it can store these nodes. So this is a node type of pointer. So this is a double pointer I should take. Means this pointer is for array and this is for pointer of type node. It's going to store pointer of type nodes. Then this queue structure, then here. When we are creating an array, it is not integer type pointer. It's a node type pointer to a pointer. That is double pointer. I'll hide this panel. Then the number of elements are size, and it should have size of node type of pointers. So it's an array of pointers. So the array is created like this dynamically from heap. Then enqueue function, I have to modify it. Element it should insert is node type of pointer. Then dequeue should return me node type of pointer. Yes, and this x should also be node type of pointer, and it should be initially null. It's not -1, it is null. So I have done sufficient changes that are useful for making this queue useful for tree. Now let us go to the main function. Now outside the main function, I will create a pointer of type node as a global variable so that it can be accessed anywhere, so it's easy for accessing. Root, and root is initially null. Now we will see create function. Create. So as I have explained you, the same way I will write on the code here. So I need node pointers. So let us temporary pointers like p and t that I was using. Then also I need a variable for reading the data. Then I should also create a queue data structure, queue. Then I should create a queue. So for creating a queue, I should send the size. So I will take the size as 100, so that is sufficient for queue. And I should also send queue as a parameter, that is by address. First thing is I should know what is the value in a root. Enter root value. Then scanf percentile d, take the value in a variable x. Then create a root node. Root assign struct node pointer malloc size of struct node. A node will be created, then roots data should be set as x, and roots L child or roots R child assign null. So the node is ready. Then I should insert this root in queue. So queue. Root is enqueue in a queue. Now, as I have shown you, I should have a while loop. While not is empty queue. This is called by value. So just queue. Then to a pointer p, I should dequeue from the queue and take a pointer. So for every node, take a node from the queue. I should ask for left child and right child. Take the left child value and the right child value. If it is not -1, then I should insert it. So I will write on that procedure. Printf enter left child. Then scanf percentile d, take data in x. And if x is not equal to -1. So as I said that if it is -1, we assume that the value is not there. X is not equal to -1. Then we will create a node, t assign. I should create a node, so that code is here. I will copy it and paste it here. So the node is created. Then t's data should be set as x, and t's L child as well as t's R child should be set as null, because this will be inserted as a leaf node. Then P's L child, that is left child, should be set as T. And also this new node, I should insert it in a queue. Ampersand Q, this T is inserted in a queue. Now, as I have done for left child, the same thing should be done for the right child also. So copy this code and paste it here. Now, instead of saying left child, just say right child, enter right child. And this P is right child. That's all. Everything is same. So this is a little lengthy function for creating a tree. And root is a global variable, so it's accessible everywhere. So I can directly call create function. Now here inside main function, I will simply call create function, which should create a tree. Then after that, for displaying, I should have a function for preorder traversal, and to that I will send root, and I will write a recursive function here, void preorder struct node star p, and if p, this is the simple code that we have already seen, printf percentile d with some space, p's data, print data, then call preorder upon p's left child and call preorder upon p's r child. That's all. Now, after creation of a tree, I am calling preorder function. So main is having just two calls to functions create and preorder. And one thing, on the top, I should include the header file, that is q.h I have included. That's all. Now let us compile and run the program. Oops, I got an error. Redefinition of create. We have written a function called create for q. So I will change this create function. This is a tree create, so I will call it as tree create function. And inside the main function also, I will call it as tree create function. Now let us run this. Now the program is running. Enter root. So root value is 10. Now root value, is it having value? Left child? Yes, 20. Is it having right child? Yes, 30. Then enter left child. Who's left child? Oh, I missed this one. I should give a message. I'll stop this program and I will show here, that is whose left child we want to find out. So enter left child of percentile D. So here I will print P's data so that I can know whose left child we are asking. And even here I should make a change when I am asking for the left child of percentile D. So I can know whose left child and right childs are being asked. Now let us run the program. It's asking for the root value, so root value is 10. Then enter left child 20, enter right child 30, enter left child of 20, that is 40, then right child is 50, left child of 30 is 60, right child is 70. Then after that I don't have any node, so -1 I am entering, so it will not do anything. It will not create any nodes. Now this is the pre-order traversal. You can see this 10, 20, 40 and 50, 30, 60, 70. These are coming on the right hand side. These are coming on left hand side. 10 is root. So this is the pre-order traversal. That's it. So I will include one more function, like this is for the pre-order. So I will write two more functions, and that is for in order and post order. Copy this. Instead of pre-order, I will just name it as in order, and this printf should be in between. So cut this one and paste it here. Now instead of pre-order, this is in order. Now this is post order, post, and printf should not be there. And this is post order function. This is post order function. Now at the end, I should print the value yes. Now after pre-order, I'll give a new line and then print post order, new line, then this is post order. I will call the function that is post order. Post order, O is small, passing root. Now let us run and check. I'll give only few nodes. Root value is 10, okay. Left child is 20, right child is 30. Then after that I don't have any nodes. -1, -1, then -1, -1. See, pre-order is 10, 20, 30 and post-order is 20, 30, 10. It's perfect. So that's all in this video. We have seen how to create a tree. It was quite lengthy because I have to prepare queue also that is useful for creation of a tree. That's all in this video. In this video, we will write a program for trees using C++. Now, for creating a tree, we require a data structure that is queue. We have already done that in a C language program. So here in C++ program also we will use a queue for creating a tree. And in this program, I will not be writing the code once again, but I will be copying the code from C language program which we have already seen. Because the procedure inside the function will be same, only the thing is we have to write a C++ class for a tree. So I will copy this code for queue. This is a class for queue which we have already implemented in previous videos. I will use this class in my new project. So I'll copy this one. Let us start a new project. I'll call the project name as tree CPP and let us select the language type as C++. Project is ready. Now here in the project I will insert a new file. So I will say new file and let it be a header file. In this header file I'll keep a class for queue. Header file, let us call it as queue.cpp, and this header file I'll paste the code that I have copied there. So this is a class for queue. Yeah, here this class is using still printf and scanf because I did not change them to scene and cout. So this class needs stdio.h, so I will include stdio.h hash include. Now this queue class should be using a node for a tree. So I will define a class for node here itself. Class for node. I'm saying node. This node will be for a tree. So this node will have 3 members. So I'll make those members as public so that I can easily access them. First is a pointer to a left child. And next is data that I want to store. And third one is a pointer to a right child. So our child. Now this class is for node. So this is a node of a tree. Now this queue should work upon node. So I should modify the code for this node because I may be storing the addresses of the nodes in a queue while creating a tree. So here I will make changes. This array should be of type node pointer. So node pointer. So already it's a pointer, so double pointer. Then here inside the constructor, when I am creating an array, I should not say int, I should say node pointer. And one more place I have mentioned this is a node pointer. This queue class should store the addresses of a tree, so that's why I am converting into node. Enqueue, it should not take an integer but a node pointer. Here also enqueue, I should change it. So I'm making required changes, and dequeue should return a node pointer. In dequeue return type is node pointer, and this variable where I am taking the data, it should be of node type and I should initialize it to null. This display function, though I don't need it, let it be, I'll just leave it. I don't have to make any changes in this function. So that's all, I guess. These are the changes what we need in a Q class. So we have made required changes. Now let us go back to the main part of a program, that is main function. So here I should write a class for tree, class for tree. Now inside this I should have only one data member, that is root, pointed to a root node, that is root. Now the question is, shall I make it as a public or private? I may be using it from outside the class also. I suggest this should be made as public. If it is made as a private, then I have to make a lot of changes in the code. So let us declare it as public. Now inside this, the first thing is constructor. So constructor class name is tree and non-parameter is constructor, and just I have to initialize it to null. Root is initialized as null. Then no need of any constructors. Now I will write down required methods. First one is create tree function, which doesn't take any parameter because root is available inside tree class itself. Then next function is preorder. I'll take capital P, and it needs a root pointer. So let us call it as P, pointer P, void post order, and it also takes a pointer to a root, that is, let us call it as P. Then in order, take the pointer as P. These functions we have already written in a C language program, so the same set of functions I am making them as member functions of a tree class. Then also I will write on one function for level order function, and it also takes a pointer to root, and height function, height, which takes a pointer to root. That's all. These are the functions I am going to implement them outside. But as I said that I will not be writing the code once again. I will not be typing the code once again. All these functions, I'll copy them from my C language program and I'll paste them and use them here. So let us first bring the function, that is create a tree function. So already I have that project open here. So this create a tree function, I'll copy it. First function I will copy it and I will use it here. And also I will make all required changes. So just watch how I am making changes in this one. This is tree create function. Actually I am calling it as create a tree. Okay, I'll change the name. This is inside tree class and this is create tree function. Okay. Then inside this is not a structure node, so just a node. I need temporary pointers. Then Q, already a class is available, so I have to create an object of Q. So yes, Q object will be created. For this one, here on the top, I should include header file, that is include Q cpp.h. This is the header file. Now I can use that Q. So if you see this header file, this qcpp.h, this header file where I have the Q as well as the node structure for a tree is defined here. All those things I'll be able to use them in my main part of a program when I have included this header file. Now line by line, let me continue. Here I was creating a queue of size 100, so instead of calling a function create, I will just call parameter as constructor of queue class, so a queue of size 100 will be created. And it will be a queue of pointers of type tree node. Then here this goes regular, and here instead of saying malloc and size of all those things, I have to simply say new node. So I'll replace this with a code that is new node, and rest of the things are as it is. Then enqueue. So this is a part of queue now, queue.enqueue, and I don't have to pass this as parameter, just a root as parameter. See, this is a function, enqueue is a function inside the class, so queue.enqueue I have to say. And here, while not is empty, oh, I have not implemented is empty function, so I will be implementing that is empty function there. I'll do it afterwards. Is empty function inside a queue class. Then q dot dq, I should say, I should not pass this anything as a parameter. Then printf, let it be as it is, no problem. Printf and scanfs will be using as it is. I will not change them. So for that, I should include stdio.h. I can use printf and scanf. So this is printing and reading the value, and the value is so and so. And if the value is -1, then don't insert anything. If it is not equal to -1, then create a new node. So for this, I will call it as new node. Then node is created, all the links are set. Then call q.enqueue, change this one. Now again printf scanf, everything is as it is. Then this part should change, that is new node. And again here q.enqueue, remove this q as parameter. That's all. This function is ready. Tree create function is ready. One thing I have to write down is empty function, so I'll go to this class and here I will introduce a function that is empty just after dq. This should return true or false, is empty, true or false. So for what is the condition for q empty? If front is equals to rear, then q is empty. It should return the result of this condition directly. Return front is equals to rear. If front is equals to rear, it returns empty. Yes, true. So this is sufficient. So I have implemented it as an inline function that is within a class itself. Now coming back to the program, see here I have implemented create function. Then I need pre-order, post-order, in-order. So I will copy those functions and I'll modify them here according to my CPP program. So here I have those functions, pre-order, in-order, and post-order. So I'll copy all these functions. Yeah, here inside the main part of a program, after tree create function, I will write down those functions. All these three functions, I need them. Pre-order. This is the part of a tree. Just now have declared it here inside a class, right? Pre-order, right? Same function. I'm writing it as a part of a class, so I am using scope resolution. Then what is the change inside this? Just printf. Instead of printf, I can use a cout. Let it be printf only, so there is no difference. So just it has become a part of a tree class now. Then in order also I made it as a part of tree class. Then pre-order, post-order also I made it as a part of tree class. No more changes at all. See, as it is, the code is useful. Now it was earlier in a C program, it was an independent function, but now it has become a part of tree class. That is the difference here. Let us bring other functions, that is level order function and height function. There's a level order function. Count and height is also there. So I'll copy these and paste them here. So count I have not declared. I'm not using it. I'll remove this one. Then height and level order. Now for height, directly I will change this one. This is height, capital H I have taken, and this is a part of tree class. So just say tree, and here inside this also, this is capital H and capital H. That's all, no more changes. Same code will work for this class also. Now let us come to level order. For level order, I should call it as a member of tree, so scope resolution. Then here inside this, again a level order function uses a queue. So I have to use that queue class, this class which we have written here inside the header file. This class I have to use. So for making use of this one, I should make required changes. First of all, I'll take a queue, that is a object of queue class, and I will take it as a constructor as 100. So I will remove this one. I will not have create function. Then printf is there. Let the printf be as it is. Then this is enq function that was in C language, which was taking q as well as the value to be inserted. But now it will be a part of q class, q object. So say q dot and root, no need of any parameter. Then this is q dot is empty. Don't pass it as parameter. Then q dot dq is there. So q dot dq. Then L child, R child. Then this is q dot nq and no need of this parameter. And here also q dot nq, no need of q as parameter. That's all. Now main function I have to write afterwards, but till here let us compile and check, are there any errors? If there are any errors, I will remove them. See, the approach what I have taken here is I have copied the existing code and I have prepared a class for tree without writing even a single line from the scratch. So only the class I have written and I have implemented all the things that are borrowed from the existing code. So I may get errors. So just watch if there are any errors, how to remove them. I'll compile this one. Yes, there are 4 errors. First one, level order. See, it is not matching here. See, inside this class I have given small letter O. This is capital letter O. Okay, I will change it to small letter O. Let me compile once again and see how many errors I get. Okay, still 3 errors. Now coming to this height. Okay, for height I got an error. So height, actually it is returning integer type. So it is giving an error that return type of outline function is different. So let us go back to the class definition and see. Oh, height I have written it as void. So it should be an integer. It will be returning an height. I'll compile it once again. Yeah, it's successful. Now I will write down a main function. Inside a main function, let us create a tree and call traversal functions. So tree t. T is a tree. Now on tree, I will call function create tree. Let us check the function. Yes, create a tree. This function I am calling, which will create a tree. Then after this, I will call just preorder function. Now to this preorder, I should pass a root because it's a recursive function. Definitely it needs some parameter. It cannot be without parameter. So I should pass t dot root. T dot root. Root is a data member of a class tree. Yes, this is a data member. Can I access this? Yes, it is kept in public. That is the reason I have made it as public, so that I can access it directly. Otherwise, I cannot write recursive function directly. I need some dummy functions which will call these functions indirectly. I'll show you that one. If I don't make it as public, then I cannot call these functions that are recursive function directly. For them, I need some other dummy functions. I will show you how to do that. Later, I'll show you how to make this as private. So let us go to this main function and complete it. Yes, I am calling preorder. Now let us run the program and see. I will create a tree and it should perform preorder upon it. Yes, program is running. It's asking the root value. Root value I will enter it as a 10. Now left child of 10 is 20, right child of 10 is 30, and there are no more children. Yes, I got a pre-order. 10, 20, 30 is a pre-order. It's working. Let us perform in order also and check. T dot root, I will pass it as parameter. Now run it. The program is running. It's asking for the root value is a 10 and the left child is 20, right child is 30, and no more children beyond this. Yes, this is the pre-order. 10, 20, 30 is the pre-order and 20, 10, 30 is in order. So let us make it properly. Let me give a proper labeling here. Before this pre-order, I will give a message that is, this is pre-order with a gap. Then after pre-order also I will give a new line and L. Then after this I will say in order, then with a gap. Then after in order again I will give a new line C out and L, that is new line, one more new line. Yes. Then when I am using C out here, I should use using namespaces. I should declare in the beginning. Already I have done it. Let us run the program. Now enter the values. Root value is 10 and its left child is 20, right child is 30 and no more children. Here you can read it. That is pre-order is 10, 20 and 30 and in order is 20, 10 and 30. Yes, it's working. That's all. Now, as I said that I can even make this root as private so that it's accessible only inside the class. Then how to write this recursive function, how we can pass the parameter. So for this, I should have one more pre-order function that is without parameter, and it should call this pre-order function by passing root as a parameter. Now let us call this function pre-order function. So you can see that this is a non-parameterized function and this is parameterized. So these are overloaded function. So from this function I am calling second one, this function, by passing a root. So from the main function I cannot pass root, so I will call this function and this will call a recursive function by passing root. So let us call this pre-order function from here and check. I am not passing root as parameter. Now let us run. It will work. Yes, it is working. So if I give the values 10, 20 and 30, then minus 1, minus 1, minus 1, minus 1, it's working. Pre-order is executed. So the same function has executed. So if you check here, I am calling the first function that is without any parameters, and that function is calling a function with parameters. So in the same way, for all these functions, I should provide a dummy function which without taking any parameters. Then I can make this root as private. So I will write down all those and I will show you finally. Yes, I have written a dummy function for each and every recursive function. So these dummy functions are calling those recursive function internally. I can make this as private now. This root, I can make it as private. So I'll just declare it above public, so it becomes a private. Now from here, I don't have to call function by passing root. Directly I can call the function. A dummy function will be called. That in turn will call a function that is recursive function. So for all of them I have given dummy functions. Now I am able to make it as private. This is the approach you have to take. If I run, it runs successfully. I'll not give the values now, already we have seen it. So that's all in this program. Oh, there is some warning, it is showing some warning. Let us check the warning. Okay, here it is giving a format specifier error. Yeah, we are displaying addresses here, but it is a D is written here. Anyway, this is a display function. We are not using it. We don't need it. So let us ignore it. That's all in this program. So you have seen how we can write a C++ class for a tree. So you can write on this by yourself. If you have implemented those functions, you can borrow them here and you can avoid typing the whole program once again. So that is the reason I am having printf, scanf as it is used here. You can change them to C in and C out also. So that's all in this video. In this video, we'll look at recursive functions for tree traversals that are pre-order, in-order and post-order. So already I have an example ready. Let us start with pre-order. For traversals, I have taken an example tree with a linked representation. These are the nodes with the data inside the node, and this is the address of a node. Below each node, its address is written. This is a recursive function for preorder traversal. So let us read the function, then I will show how this function will find out preorder of this tree. See, function is taking a parameter, that is root of a tree. So we will pass root to that one. Suppose if you are calling, then we call it as preorder root. So we will pass the address of the root node, that is 200, to this one. So here the parameter name is t. Then inside the function it will check if t is not null. Means there is some node. If there is some node, then it will perform 3 steps. Print the data from that node. Second step, call itself recursively upon left child. Third step, call itself recursively upon right child. So these are the 3 steps it will perform. As it is recursive, it will call itself again and again until entire tree is traversed in preorder traversal. We already know how recursive function works. We have seen their tracing. We have generated the tracing tree. And we also know that stack is used by recursive function. For each call, activation records are created in the system stack. So similarly, let us trace this preorder function upon this tree. So let us generate a tracing tree. So for tracing tree, I will take a stack also. So here I will create a stack, that is system stack, to show how the activation records are created for each call. Let us start tracing that function using tracing tree. First time when the function is called by passing root, root is the address of the first node, that is 200. So the function is called with the address 200, pre 200. In short, I am writing just pre. First call, pre 200. So as root is 200, 200 is passed. So once the function is called, an activation record is created. Activation record will contain all the variables that are used by that function. So what are the variables used in a function? Only t is used. So that is the address. So I will write down just address 200. So activation record will be created where t value is 200. Then let us execute. First statement, t is not null. Yes, 200 is not null. 200 is not null. Then perform 3 steps. So 3 steps. First step is print data. Print data of this node 8. Then second step, call itself again on left child. Left child address is 210. Call itself again on 210. Then next third step, call itself again on the right child. We will do it afterwards. First let us finish this one. So this call, what happens? Again an activation record is created with the t value as 210. Before continuing, let me write down the output that we got. So far, value 8 is printed. Value 8 is printed. Now, for this call, 210, let us start the procedure once again. 210 is not null. Yes, not null. 3 steps. Print, call on left, call on right. Print data. So, 210, value is 3. Then call itself again upon left child. That is 270. Call itself third step upon right child. We will do it afterwards. First of all, this has to finish. Now for this call, activation record is created. This is with 270. For this 270 and the function is called again t is not null. Yes, it is 270. It is not null. Perform 3 steps. So 3 steps. We know the step very well. Now I will not be checking every time here. We know the steps. Print, call upon left side, call upon right side. I will be following these 3 steps every time. So now this is not null. So print the value 4. Call itself upon left child. What is left child? Null. This is null. Just I am writing P here for preorder. Then again an activation record is created with null. Now this time T is not null. No, it is null. So it will not enter into this if and ends. So this function terminates without doing anything. So its activation record is deleted. Once this is deleted, it will go back to the previous function call. Previous function call was 270. In that function call, out of 3 steps, 2 steps are completed. Printing and going on left child. Now what is remaining? Go on the right side. So P of, what is right side here for this node 270? It is here at 270. So right side is null. Right side is null. So again it will call itself with null. So again the activation record is created at the same place. A new activation record is created with the t equal to null. But this call is different. This was over already. This is a new call. So again for this call, T is not null. No, T is null. So it will not enter inside if nothing is done. So this will terminate. Once this terminates, its activation record is deleted and it goes back to the previous function call, that is 270, back on this one. As per 270, all three steps are completed. Three steps are completed. So this is also completed. Go back to the previous call, 210, this one. For this call, two steps are over, printing and calling on left side, this one. Now it has to call on right side, that is 300. So it will call itself upon right side, that is 300. So for 300, a new activation record is created at this place for different function call. Now this is not null, three steps. So I'll perform those three steps quickly. First one is print the value. So what is the value? 9. 9 is printed. Then call itself again for left child, that is 0. So activation record is created once again. But this terminates. So this is over. Back to this one. Third step, call upon right child. This is also null. So new activation record is created. This is null. So this terminates. So this is over. Go back to this call. This call, three steps are over. All three steps are over. So this call finishes. So this ends. Now it goes back to 210. This one. For this one, all three steps are completed. Printing, call upon left child, call upon right child. So below this, there are more steps that are finished. These are also finished. So this function call has finished. So it will go back to previous call. This one, main call. So out of this, two steps are completed, third step is remaining. So I'll stretch this little more here. So third step it has to perform, that is go on right child. PRE upon right child. Right child is 230. So new activation record is created above this one with a 230 for this call. This was already completed, 210. So it is calling this one. This is not null. So not null means three steps it has to perform. Print the value, call upon left child, call upon right child. So print the value. So what is the value? 5. Right? Then call upon left child. Pre-order of left, that is 310. Right child afterwards. First 310. A new activation record is created with 310. For this again not null, three steps. So print a 310's value. What is the value inside that? 7. Then call itself for null. So T assign 0. New activation record is created. But this ends. So this is terminated. So this is deleted. Goes back to this call. Again P0 is called for right child. T0. This terminates. It ends. Goes back to this call. This is completed. So this is deleted. Then go back to this call. 320. So P for right child. 320. For this one, it will print a 2 and it will call itself for 0 and 0. Okay. So two more zeros are created. Then they are deleted. This is over. So 320 is finished. Then 230 is also finished. Then this is also finished. Did not write the output. Let us check and write the output. First 8 was printed. Then 3 was printed. Then 4. Then 9 was printed. Then 5. Then 7. Then 2. So this is the output of pre-order. So tracing tree, it has expanded like anything. So once you know how this tree is generated, if you are familiar with this tree, you can even work out upon this tree structure itself. You don't have to generate a huge tree, but you have to do it at once. Then you get the idea how to do it directly upon the tree. Now let us analyze the tree. First of all, total how many calls are there? Let us check the number of calls. 1, 2, 3, 4, 5, 6, 7. Then 8, 9, 10, 11, 12, 13, 14, 15. Total 15 calls. Actually, if you see these with addresses that are equal to nodes, and these nulls are for nulls. So if you remember, we already saw that if there are n nodes, there will be n plus 1 null pointers. So total number of calls are 2n plus 1. N for number of nodes, then n plus 1 for number of null pointers. So total number of calls are 2n plus 1. Then once again I will show you in which order the calls are made. This was the first call, second call, third and fourth call, fifth call. Then this was the sixth call. Then this was seventh call and eighth call. Then go back and come this side. This is the ninth call, 10th call, 11th, 12th. Go back and come this side. 13th call, 14th and 15th call. In this order, these calls are made. If you know in which order the calls are made, then you have understood the procedure, how it is working. Then let us look at the stack. How many activation records were created and destroyed depends on the number of calls. Total 15 calls. So 15 activation records were created and destroyed. But you see, at a time, how many activation records were there? 1, 2, 3, 4. 1, 2, 3. 3 levels are there. Plus 1. Because for nulls also calls are made. Right? So it depends on this vertical dimension of a tree. That is height of a tree. No doubt it is 4 but the height is 0, 1, 2. Height is 2 only but they are 4. Don't go on count. Don't go on count. It is dependent on height. So I can say that the size of the stack will be height plus 2. Whatever the height may be. So if I write height plus 2, then I can say that it is dependent on height value. That 2 is constant, always 2 you will be adding. So the actual size depends on height. So yes, saying that depends on height is not wrong, right? So don't go on the count always. So how many activation records are created? What is the size of the stack? It depends on the height of a tree. That's all. This is the procedure I have analyzed. So in the next procedure, in the coming procedure, I may not be showing stack every time. You know how it works. I'll try to keep the same example so that you already know about this and you already know the tracing tree. So with the minimum work, I will try to show the tracing of remaining functions upon tree. Let us look at in-order traversal upon a tree. So already I have a tree available here and a recursive in-order traversal function. This is a recursive function. It's similar to preorder. What is the difference? Function name is different. Yes, it is in order, so function name is different. Then 3 steps. Yes, it is having 3 steps. But if you observe, in preorder, printf was in the beginning. First step was printf. Then preorder calls were there. 2 calls were there. But now 2 calls are these calls and the printf is in between them. So it is in order. So guess how to write post order? Printf should be at the end. Yes, printf should be at the end. That's post order. Now let me show you how this function works upon this tree. So I will just show you the tracing tree of this function. I will not show the stack. Already we have seen detail in preorder. So let us just generate tracing tree and understand how in order is working. Here I will be writing the output. First time when the function is called in order, first time the address of this root is passed, that is 200, right? So first time when we call it like this, in order, and we pass root. So 200 is passed. So it will take the address. Now wait a minute. Function takes addresses, but addresses may confuse us. From the tree, if I ask you to read, you will try to read values only, data only. So we prefer data. So addresses may confuse. So instead of writing addresses, I will write on data. If at all anywhere required, I will write on address. We know addresses are passed, but I will try to write data. So instead of 200, let us say it is called upon a node in which data is 8. So that makes sense to us, right? So let us continue. This is not null, so it has to perform 3 steps. First step is call itself upon left child. Second is print the data. And third is call itself upon right child. So the first step happens, that is calling itself upon left child. So left child is 3. So it will call itself upon left child, that is 3. And the second step, printing, it is done afterwards. Let us finish this. Then calling upon right child will be done afterwards. First let us finish this function, that is in order upon node 3. Now for node 3 it is not null. Yes, again 3 steps. Call upon left child, print and call upon right child. Call upon left child, print and call upon right child. So first step is call upon left child. In order of left child node is 4. First it will call itself upon left, then other two steps. First let us finish this, then we will perform other two steps. Then what about with value 4? It is not null. Again perform 3 steps. So go on left side. So this time it will be null. In order of null. In order of null, nothing will happen. Then what is the second step? Print data. So this time it will print data. Value 4 is printed. Then what is the next step? Go on right side. So what is there on the right side of 4? Null. So again for the right side also it is in order of null, then nothing will happen. See, this is not value 0. Actually I am showing values here. But here I have to show null, so I am writing 0 to show that this is null. Next, this has finished. It will go back to this node, that is third node, this one. For this, first step is completed. Upon left side everything is completed. Now the next step is print. So it will print data. The value is 3. Right here already we have the value 3. So first value that was printed was 4. Now the next value is 3. Then third step it has to perform. That is go on the right hand side of 3, node 3. What is there? It will call upon node 9. Again 3 steps. Go to left, print the value, go to right. For left it is null, nothing. So print 9, 9. Then go on right side, there is nothing. This is completed. So this is also completed, all 3 steps. Go back, then here, print 8. This is the step remaining. See, this portion is completed, totally completed. 8, print 8. Then go to right side. So for right side node is 5. In order of 5. For this, go to left side. In order of 7. Other 2 steps are remaining. For in order of 7, left side, in order of 0, nothing is there. Then print 7, in order of 0, nothing is there. So 7 is printed. This is completed. Go back to this one. Print 5. Call upon right side. Right side is 2. 2. For this, upon left side, nothing is there. Print 2. Then upon right side, nothing is there. So this nothing, they all terminate, right? So the values that were printed after this was 5 and 2. So the output is 4398752. Let us do it directly by moving finger around it. I said that for in order, keep your finger on the top of this node, right? Put it in this direction, right? Upward direction. So let us move around. We reach the bottom of 4, then get inside. We reach the bottom of 3, yes, 3. Then bottom of 9, yes, 9. Then get inside. We reach the bottom of 8, 8. Bottom of 7, 7. Bottom of 5, 5. Then bottom of 2, 2. Finished. So answer is correct. I have shown you 3 methods. In all 3 methods, I was taking the bottom of a node, right? So if you observe here, in order, see, printing is done in between. Printing is done in between left child call and right child call. So between left and right child, printing is done. So that's how, if I move a finger around like this, see 4, then 3, then 9, then 8. This is what I have shown you. In pre-order, if you observe or if you go back to the previous video and watch, pre-order printing was done first. So it was on the left hand side. What happens to the post-order? Printing will be done afterwards. Yes. So if you want to modify this function, write down printf at the end. That is post-order. So I don't have to show you post-order. Post-order is a student exercise. You can do it. It's a small function. You can write down that function. So printing will be done afterwards. Now let us do some analysis. Total how many calls? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 calls. We saw them in pre-order also. 15 calls were there. How many nodes are there? N nodes. 7 nodes are there. Right? Then how many null pointers? N plus 1 null pointers are there. So for each node a call is made, and also for null pointers calls are made. So total calls are 2n plus 1. So total calls are 2n plus 1. Now one thing I have to tell you, I did not say that in pre-order. What is the time complexity of this traversal? It depends on how much work it is doing. What the work it is doing? It is calling, and every call it is trying to print if possible. Just printing, one step only. How many times it is printing depends on the number of calls. So how many calls are there? 2n plus 1. So what is the degree of this polynomial? N. So the time complexity of traversal is n. Remember this, the time complexity of all the traversals or whatever you do upon a binary tree, most of the time it is n. Now next, let us look at the order in which the calls are made. See, this is the first call. This is the second call, third, fourth call, fifth call, go back, sixth call, then come this side, seventh call, go back and come this side, eighth call, go back and this side, ninth call, 10th call, 11th, go back and call this side, 12th call, 13th call, 14th call, 15th call. You can observe that the order in which the calls are made is same as pre-order. In pre-order also same thing was happening because the function is calling itself 2 times upon the same tree. Then same amount of calls will be done. But the difference in pre-order and in this one is printing was done beforehand, printing is done in between 2 calls. That's only the difference. So the calls will be same only. What will be the size of the stack? Size of the stack will be same. That depends on the height of a tree. Height plus 2 we analyzed that time. So the size of the stack will be height plus 2. So you can say order of h. That height of a tree, if you remember, height of a tree can range from log n to n, where n here is the number of nodes. So in our example, the height is log n. But if it is a skewed tree, then the height will be n. So it depends on the height. So usually we don't write order of h, any other variable we don't use, we use n only. So that h means either it can be log n or n. So minimum is log n, maximum is n. So that's all about in order, and post order also gave you the idea. You have to write on the function for post order. In this video we will learn how to write iterative tree traversals. We have already seen recursive tree traversal, we have seen recursive functions. Now we will write iterative functions for pre-order, in-order and post-order. Recursive functions we already saw. So if you want to convert a recursive function into iterative function, that is a function with a loop, then you may have to use your own stack. It's not necessary always. In some procedure, that depends on the procedure. So in some procedure, you may need to have your own stack. Means you have to use your own stack in iteration. So that's what this is the exam. In this example, we are going to use a stack. Without stack, we cannot convert recursion to iteration. So first of all, I will explain you the procedure. Then after that, I will write a function also. So let us start with the pre-order. Let me show you how we can perform pre-order iteratively without recursion. Let us perform it upon this tree. As I said, I may require a stack. So beforehand, I will draw a stack and keep it ready. Maybe it is useful. And here I am going to write on the output. And one more thing is, pre-ordered steps are first print, then perform pre-order on left child and perform pre-order on right child. That is root, left, right. So root means print. So first print, then go to left side, then go to right side. So let us start and follow these steps. Okay. So let us start from root node. T is here. This is the root node. What is the first thing I have to do? Print data. So I will print that data. 8 is printed. Then move on to left. Okay. I am moving on to left. Okay. Then on this again what I have to do? Print data. Okay. Print 3. Then do what? Go to left side. Okay. I'll go on to left side. Then print data. First step here is print data for this node. Then go to left side. Okay, I will go on left side. Now T became null. Now do what? Go to right side. Watch carefully. Go to right side. Whose right side? This node's right side. Do you have the address of that node? No, T is there. So what is T now? T is null. Null means it is nowhere on the tree. So T became null. How do you get the address of this node? The address of this node is with this node, and this address of this node is with this one, and that is with root. So I should again come from root. That's what. This is the problem. So I should go back to this node, and again remember, I should go back to this node also to go on the right side. So I need those addresses. Then how to know those addresses? I should have pushed them in the stack. Yes, that's what I missed. So let me start over once again. I'll remove this. Let us start. T, first step, print data, print 8. Then what to do? Go on left. Going on left, but again I have to come back on this node so that I can go on right. So I need the address of this node. So I have not written addresses here. So I will write down address of that node 8, whatever the address may be. I don't know, right? Then go to left child. Okay, now move T here. Now what to do with this node? Print data. Okay, print data 3. Then you have to go on left. But before going on left, push the address of that node containing data 3, address of that node into the stack. That's perfect. Then go to left child. What to do here? Print 4. Push the address of this one into the stack. After pushing, go to left child. Now T became null. T became null. See, T is null, but stack is not empty. Stack is not empty, right? Okay, continue. What I want the address of this node. Pop out the address of 4. Go to this node. So pop out and give it to T. So T knows the address of this node now. It's standing here, right? So when it's standing here, go on the right side. So the step is pop out, go to that node and move to its right child. Then continue. Again null. See, T is null, but the stack is not empty. Pop out an address. That's what? Address of 3. Okay, go to this node. Then move to right side. Now continue. For this node, what we have to do? Print. Push the address into the stack. See, only one address is there in the stack. So here it will be inserted. Then go to left side. It is null. If it is null, what we are doing? Pop out an address. Take T upon that address. And then move T upon right side. So right now also it is null. It is null and the stack is not empty. Pop out this address 8. Take T over there. Okay. Then move to the right side. So whenever it is null, we are doing this. Right? Now continue. T is not null. Yes. So what to do? Print 5. Right? And push the address of that 5 into the stack. Address of 5 into the stack. This is the free space now. Then move T to left child. Again T is not null. Do what? Print 7. Go to left child. Before going to left child, insert the address of 7 into the stack and go to left child. T is null. Null means what we are doing? Pop out the address, go to that node and move to its right child. So whenever T is null, we are doing this. Again T is null. Pop out the address, go to that node and move to right child. T is not null. When not null, print 2. Go to left side. For left child, again push the address of that node. When you are going on the left child, put the address and go to left child. T is null. Pop out an address. Go to that node and move to right child. So T is again null. Now T is null and there is nothing in the stack. There is nothing in the stack. So we have finished the procedure and we got the result. This is pre-order. So this is how the procedure works. So when to stop this procedure? When T is null as well as the stack is empty. Now let us verify our result. Pre-order. I'll just trace with the finger and show you. Pre-order, as I said, we should point the finger in this direction. Left hand side of 8, yes, 8. The next is 3, yes, 4. Then get inside. 9, then get inside. 5, then 7, then 2. Yes, it is perfect. Now I have to write on the program code. So already I kept few things there. A function pre-order taking pointer T upon root and a stack is also available. Assume that stack is already initialized. What are the steps? We were repeating the steps. How long? T is not null and stack is not empty. Okay. So repeating the step means I will write on while loop. While T not equal to null, or it's not and, or not is empty st, stack is not empty. So while T is not null and the stack is not empty. If T is null, false. Stack is also empty, false. Both are false, it will stop. So I should use or. Then the steps. The steps are very simple. If T is not null, let us see the step again from here to get the idea. If T is not null, print data, push address, go to left child. Right? If it is not null. So here, if T is not null, then three things. Print data, push the address in the stack and move to left child. Print data, push T into the stack and move to left child if it is not null. If it is null, else what we should do? Else what we should do? See, when it was null, what we were doing here? What we did at that time? When it was null, we pop out an address and go to right child. So pop out an address from the stack, pop out an address from the stack and go to right child. That's all. End of loop, end of function. That's all. This is the iterative function for preorder traversal, which is utilizing a stack. And one more important thing is the stack should be of which type? Integer type, character type. Which type? It is storing the addresses. So it should be of a type address of this node. So while writing the program, I will show you that. Next, with a small change, I can convert this procedure for in-order traversal. So let us look at in-order traversal. Let us see in-order traversal. In-order traversal says first go to the left child, then print, then go to right child. So left, root, right, that's how we read it. Let me quickly trace this and show you. We need a stack and we start from root, then. So initially that T is not null and the stack is empty. Now let us look at this preorder. See, preorder, first if T is not null, yes, first step is printing. But in order, first we go to left child. Then we should not print. Okay, let us move to left child. But as per preorder, first push the address and go to left child. Okay, push the address of that 8 and go to left child. Okay, we will go do this. Then again T is not null, print. We will not print. This step will not perform. Push and go to left child. Push the address of 3 and move to left child. Okay, move to left child. Then this is not null again. So push the address of this 4 into the stack and go to left child. Now this is null. If it is not null, these steps we are performing, we were not performing this printf. We were performing two steps. Now it is null, else part. So in this preorder, what we are doing? Pop out, go to right child. Watch here. Pop out, we'll get the address of 4. Now before going to right child, we should print. Before going to right child, we should print in order. So printing should be done now. We are about to go on right child. See this, about to go on right child. So before that, first you print. So it means I should print here first. So print this first, then move T to R child. So printf is removed from here. That's all. So with a little bit of observation, I can say that in preorder, before going on left child, we were printing. But in order, before going on right child, printed. So this function becomes in order. So a minor change has made it in order. That's all about in order. One thing I want to show you, what is the time complexity of this function? In preorder also we saw, and in order also, same function, just a change of position of printf function. Just a minor change is there. So what is the time complexity? Loop is there. Loop. How long? As many nodes are there, that many times it will repeat. So what is the time complexity? Order of n. Order of n. And what was the size of the stack? Depends on the height of a tree. Yes, stack depends on the height of a tree. Now post order. Post order is little complex. So I'll keep the same code. Let us see what about post order. Let us see post order. Post order says that first go on left child, then right child, then print data. Go to left also, right also, means you should not print here. So after finishing both left and right, we should print. So let us take a stack and trace this one. So I'll take a stack, start from here. See, the procedure will be similar to this one only with some changes. So what changes required there? To study that, we will trace it with the help of that function only. Actually, the function is for in order. But where we require changes, we will make the changes there. So I will follow that procedure only and trace it. So let us start. T is on this one. So T is not null. What is the first step? Push the address of that node into the stack. 8. Then move to left child. Okay, move to left child. So T is not null. So if it is not null, push and move left. So push the address of 3 and move left. Push the address of 4 and move left. No, it is null. So null means what we should do else? Pop out, print and go to right child. So let us do it. Pop out. So this is deleted. T is here. Print and go to right child. No, don't print. Post order means first go to right child. Afterwards print. Left child over right. Go to right child, then print. So we should not print this one. We should not print. It should not be printed. Pop out and go to right child. Okay, I will go to right child. I will go to right child. So right child is what? Null. If it is null, pop out and go to right child. So which one I get? Address of 3. Oh, 4 I did not print. I should print that 4 also. That's it. So the difference is I should push that address of 4 once again. First time it was pushed so that we can go on right side. Second time we need so that we can print it. So before going to right child, push the address of that 4 once again into the stack. Once again push it. Then go to right child. So I will write down the code afterwards. So push it again and then go to right child. Now T is null once again. Pop out. Whose address we get? 4's address. Now see the second problem. Second problem. First time we pop out, that was for right side. This time we are popping out, this is for printing. We are back on 4. Now we should print. Now how to know that that address was for right side and this address is for printing? There should be some difference. Yes, this is the problem. So what we should do, when we are pushing it second time, we should push negative address. Addresses cannot be negative. No, you convert that address into an integer and store negative integer. When you are using, convert into an address, positive address. Okay, we can do that. So push the address once again. So both the time, first time when you are pushing, push positive. Second time when you are pushing, it is negative. So positive address means go to right child. Negative address means print the data. So I will directly modify that one and you have to trace the complete working on this example tree. Okay, this is sufficient. If I explain, it will be confusing, right? So you take pen and paper and trace this function. So I will directly write on the function. So I have explained you important points in this one, that we have to push the addresses 2 times. So I will write on the code, right? That's all. With that, I will finish. Tracing you do. You take an example tree and you trace everything and generate the complete output by yourself. So that is a student exercise. I am writing the code. Pop out an address from the stack. As I said, the stack will be of integer type. So I will take one long integer, a temporary value, temp. Okay. So I will pop out a value from the stack, pop st. So I will get an integer value in a temporary variable. Now check whether it is positive or negative. If it is positive means we have to push again and go to right child. If it is negative means we should print. So first check if it is positive. If temp is greater than 0 means positive. If it is positive, then do what? Push the negative value of temp into the stack. Push the negative value into the stack. Then move to right side. Temp is having an address, but actually it is integer value. I typecasted it into an address. Then caps r child. That t is moving on to its right child. Okay, this syntax I have written. Let us see how it works. Okay, while writing the program. Once again, if the address is positive, push the negative address once again and move t to right child. If it is not greater than 0, means else means it is less than equal to 0. Anyway, it will not be 0 here. So it is less, negative. If it is negative, then what we should do? Print the data and again make t as null. So print data. So print data by typecasting that numeric value into address. So print the data and make t as null. So this is the extra work required for post order. We have to push the addresses 2 times, one for going on right side, one for printing. So positive and negative addresses we are pushing. This is the extra work that we require in post order traversal. So that's all with the iterative version of tree traversals. In this video, we'll look at iterative procedure for pre-order and in-order traversal, which I already have discussed. So I have already written a program, C language program for creating a tree. If you remember in the previous video, that same program I am carrying on, and already I have written recursive functions for pre-order, in-order and post-order. Now we will write iterative procedures, that is using loop. So for loop, I also need a stack. So already I have taken a stack header file. I have created a header file. Just how I have created for queue, same way I have done it. This is a node type pointer, double pointer, that is for array. Then I have written a function for creating a stack, which is creating a stack here. These are the functions already we have seen in stack using array. There I have already implemented them. So this push, pop, is empty, is full, all these functions already there. So this is a stack using array. This I will be using it in the iterative procedures. Now let us come back to the C program, that is main function program. Here I will write on a pre-order traversal function that is using loop, iterative version. So let us write a function. I will call it as I pre-order, and it should take struct node pointer to root. And here it needs a stack, so create a object of type stack stk. Then I should call a function that is stack create for initializing a stack. So I will send this address of the stack, as well as I will create a very bigger size so that is sufficient. So 100 is the size of the stack. Now the procedure is while loop while p or not is empty. This is empty is there in the queue also and the stack also. So for stack I have changed the name to is empty stack, and we will pass this stack. It will check whether the stack is empty or not. And here if p is not null, we will print the data from p %d p's data. Then I should push this into a stack, so address of stack and pointer p if it is not null. Then p should move on to left child, L child. Then else, if p is null, then we should pop out a address from the stack, that is ampersand stk, and take it in p. Then p should move on to right child. That's it. This is a simple procedure, that is an iterative procedure for finding pre-order traversal. Now here in the main function already I have this tree create function. Then instead of post order, I'll just change it to pre-order, and I will call this function I pre-order function. Let us run the program. Oh, function name is with small letter. I have to change this one. This is stack small c create. Let us run it. Now asking for the root value 10, its left child is 20, right child is 30. Then I don't have any other children, so all these are minus 1. Yes, pre-order is 10, 20, 30. It's working. Let us run it once again. Root is 10, left child is 20, right child is 30, and its left child is 40, then its right child is 50, left child is 60, right child is 70. Then I don't have any nodes at all. So all I have to mention them as null. Yes, pre-order is 10, 20, 40, and 50, 30, 60, 70. So left hand side is 20, 40, 50, and right hand side is 30, 60, 70. So here is the pre-order. So it's working perfectly. Now how about in order? So I will copy this function as it is. This pre-order function, I will copy it. Copy. Then paste. Instead of I pre-order, I will call I in order. And instead of printf call here, I should call it before going on the right child. Then instead of pre-order, I will call in order. Let us call a function I in order here. That's all. See, if you remember, just a change of location of printf function will change it to a in order traversal. Let us run the program. Asking for the root 10, left child is 20, right child is 30. Then I don't have any other data. So end of this one. Yes, in order is 20, 10, 30. It's perfect. So this program is a little lengthy because already you should have saved this queue and stack, and you can utilize those things here. So that's all in this video. The topic is level order traversal of binary tree. Here is an example of binary tree. Already we have learned about level order. Again I will repeat it. Level order means traversing all the vertices of a tree level by level. So first level is 8. So if I write the output here, first level is 8. Then second level, the first value is 3, next value is 9. So 3, then 9. Then next level, third level, 7, 6, 4. Then last level, 5 and 2. This is the output of level order. So how actually it is done? First visit root. Root is visited. Then visit its children. So the first child, left child, then right child. Left child, right child. Then children of left child, 7. Children of right child. Then its children. So first left child is only left child is there. So we went on 5. Right child is not there. Then the children of 9's children, that is this one, 6. So 6th child is only 2. So only 2 is visited. So this procedure requires a queue. So I'll take an example queue, and again I will traverse it and show you how a queue can help us in traversing in level order. So I have a queue ready here. Let us traverse it once again. So for that I will take a pointer P. First visit root. So that is 8. And insert the address of 8 in the queue. So address of 8. So this was the first step or initial step. Now the step is repeating step. Let us look at repeating step. Take out an address from the queue and give it to P. So that is the address of 8 only. So okay, P will point on 8, again on 8. Then visits its left child, 3. Insert the address of 3 into queue. Then visits its right child, 9. Insert the address of 9 in the queue. I'll just write 9. That is address of 9. So using P, we have visited left child as well as right child. Now it is over. Work is over. These are the steps. Take out that address from the queue. Visit left child. Insert its address. Then visit right child. Insert its address. Now continue repeating the steps. Take out an address from the queue. So the next address is of 3. So take a pointer P upon that address. Visit left child, okay, left child, and insert the address of node 7 into the queue. Then visit right child. There is no right child. If it is null, then we cannot visit. So it is completed. Then take out next address from the queue, that is 9. This is the new node. Visits left child 6, address of 6 into queue. Then visit right child 4, address of 4 into queue. Its work is over. Then delete next address from the queue and make p point on that one. Visit left child 5, push the address of 5 into queue. Then right child, there is no right child, leave it. Then take out next address 6, p is pointing on 6, left child, no left child, right child, yes 2, insert the address of 2 into queue. This is over. Take out next address 4, left child, no left child, right child, no right child. Then come on 5, 5 is not having any children. Then take out 2 and move to 2. Visit left child of and right child of 2. There are no left and right child. Now queue is empty. Queue is empty. Once the queue becomes empty, stop. So take out an address, visit left child, right child. That's all. So the procedure is very simple. But initially we have first visited root, then we have inserted the address of root into queue. Let me write on a procedure for this one. Yeah, procedure here. Queue is ready. Already I have taken a queue. Queue should be of type addresses of node. It's not an integer queue or character queue, address type queue. So the data type of an array should be node type. Okay. While writing the program, I will show you that. And also this queue should be initialized. So initializing that front pointer and rear pointer that we have to do. Next, first step I will perform. Right, p is a pointer, that is, assume it is on root, right? This is the root. Then first of all, print the data of root. Printf p is data, so p is pointing on root, so data is printed. Then insert the address of this p into q. Enqueue this address in q. Now the procedure is a repeating procedure, so I will write down loop while we have to stop when q becomes empty, so not is empty queue, means as long as queue is not empty, continue. First step is take out an address from queue, so say dq, take out an address from queue and take it in pointer p. Then print left child if it is there. If p's left child is there, then print p's left child's data and also insert the address of left child into queue. Like this node's data is printed, that is 3 is printed, and the address of 3 is inserted or enqueue in a queue. Similarly, check for the right child. If right child is there, then print it and insert it into queue. That's it. Here p is right child, means if it is not null, print the data and insert the address of that right child into queue. And this is the end of while loop. This procedure will be repeating and printing all the elements from a tree. So that's all. This is a in order procedure. In this video, we'll look at level order traversal of a binary tree. So already we have seen a program for creating a binary tree and performing various traversals. So in the same project, I am just adding a function for performing level order traversal. So let us write down a function for level order, which will take a node of type root, that is node, tree node, then. So inside this we need a queue, so I will take a queue data structure queue. Then I should create a queue also. So let us call it as create ampersand queue, and the size I will take it as 100, a bigger size, so that it's sufficient for me. Then as per the procedure we have seen, first of all we will print the data from the root. So this is data, p's data we will print. Then after printing data, we will enqueue the root. So in queue, I will enqueue the root. So p is a pointer to the root. We'll do one thing, we'll change this name from p to root, as it's a local variable, it doesn't affect actual root. So we can read it properly. Instead of p, I'm calling it as root. So root is inserted into the queue. Now, while not is empty queue, as long as queue is not empty, we will print left child and the right child, and if there is a node, we will also enqueue it into the queue. So first of all, to a root, dequeue a value from the queue, dequeue it, and if root's left child is there, then print that left child, printf %d and some space, root's left child's data is printed, and left child is enqueue. Inserted in the queue, that is root's left child. That's all. Then again, we should check whether right child is there. If right child is there, then that should also be treated in the same way. So I will copy it and paste it, and this is right child. So right child is there, then right child data is printed and it is enqueued. That's all. So after this loop, so there is nothing we have to do. So this is the level order. So that's all. This is the level order function. And now inside the main function already create a tree is already there. So now I will call level order function. Level order pass root as a pointer. Let us run this. So I will enter nodes, that is root node, and its left child is 20, right child is 30, its left child is 40 and right child 50, then 60, then 70. So I should get all the elements in the level order 10, 20, 30, 40, 50, 60 and 70. Now there are no more nodes, so all -1. Yes, I got the elements in the same order. This is the level order. That's all. So I have just added one extra function to a tree program or tree project. See, the topic is, can we generate a tree from traversals? So from traversals, we want to generate the tree. Actually, from the tree, we find traversals. So if I already know traversal, can I generate a tree? There are 3 traversals. So we want to know whether just pre-order will help us generate the tree or not, or with just post order can we find or not, or pre-order or post order, if they are given, can we generate a tree? So finally we'll find out which traversals are compulsory so that we can generate a tree from those traversals. So that's what our discussion is. Which traversals are compulsory? So let us start. I have taken 3 nodes here. These are 3 label nodes. 3 label nodes are there. Now suppose a tree with a 3 node is having a pre-order traversal as A, B, C. Now I have just a pre-order traversal for a tree with 3 nodes. Now the question is, from the pre-order, can we generate a tree or not? Let us check. For that traversal, I will draw a tree with 3 nodes A, B, C. Yes, what is the pre-order of this? First A, then B, then C. Yes, I got a tree. I am able to generate. No, let us check one more. If I draw a tree like this, A, B, C, what is the pre-order? A, B, C. I am getting same pre-order. For this also I am getting same pre-order. I try this A, B, C. For this also same pre-order. A, B, then C. Let us find pre-order. A, B, C. I am getting same pre-order. A, B, C, same pre-order. From the pre-order, if we try to generate a tree, 5 trees are possible for 3 elements. 5 trees are possible. Actually, we want one tree, one unique tree. So we cannot generate a tree. We cannot find out because there are multiple trees are possible which are giving same pre-order for 3 elements. So conclusion is, if only pre-order is given, we cannot generate a tree. But one observation is, with the same pre-order, how many different trees can be generated? 1, 2, 3, 4, 5. If you remember, these are 5 different shapes. Yes. If pre-order is given, only pre-order is given, then how many trees we can generate which are having same pre-order? 2n cn by n plus 1. Yes, Catalan number of trees we can generate. Not 1. Actually, we wanted 1. Not possible. Next. What about if I give in order? Same thing. Same thing. 5 trees I can generate. What about post order? Same thing. 5 different trees I can generate, which will give me same post order. So this is true for all traversals. If you give any traversal, more than 1 trees are possible. So how many trees are possible which are satisfying same traversal? 2n by n plus 1. Now next, shall I give you 2 traversals? Can you generate a tree from 2 traversals? I have already given pre-order. I'll give you post order also. Post order. Post order is CBA. So I am giving 2 traversals, this one and this one, 2 traversals. Can you generate a tree for those 2 traversals? What is the pre-order? ABC. Pre-order is ABC, right? What is post order of this one? CBA. CBA. What is the pre-order? ABC. Pre-order is ABC. What is post order? What is post order? From this side, right? CBA. Post order is CBA. See, more than 1 trees are having same pre-order and post order. So if you give pre-order and post order also, more than 1 trees can have same pre-order and post order. So which tree you want? Actually, we want a unique tree, just 1 single tree. 1 single tree. So with the 2, pre-order and post order also is not possible. So that's all. Conclusion is, if you just give pre-order or post order or in order, you cannot generate just 1 tree. Total 2n by n plus 1 trees are possible, not 1 tree. You cannot generate if this is given, this one or this one or this one. If I give pre-order and post order, then 1 plus I wrote, that is more than 1. There is no formula for that because there are many possibilities in this one. Many cases are there. So there is no formula for this. I cannot tell you these many are sure. No, not possible. So more than 1, that is sufficient. So if only pre-order and post order is given, more than 1 binary trees are possible. 1 tree is not possible. Then which traversals can give me tree? So I'll write them here. Yes, pre-order plus in order. Either this one or second one, post order plus in order. Any one. Why in order? Because in order will take the root in the middle. So first it gives left, then root, then right. So in order can help you. If you know the root, then what should go on left side, what should go on right side. It can help you decide the splitting of nodes in the left subtree or right subtree. That's why in order is mandatory. Alone in order will not help you. Alone pre or post order will not help you. Together pre-order, post order also will not help you. Then in order is must. So conclusion is that one of the traversal must be in order and the other traversal can be either pre-order or post order. See, the topic is generating tree from traversals. So already we have learned that any 2 traversals are compulsory. Out of that, one of the traversal must be in order. So I have a pre-order and in order. And one more possible is post order and in order. Let us learn how to generate tree from pre-order and in order. So I'll show you the procedure. Create a node. Take all the elements of in order. Take in order as it is in a node. Don't change the order. Write the elements in the same order. 7, 6, 9, 3, 4, 5, 8, 2, 1. As it is I have taken. This is initial work. Now, repeating procedure means the steps will be repeating. What to do? Scan through pre-order. Scan through pre-order by taking one element at a time. Then what to do with each element? Let us see. First step I am showing you. Take the first element from left to right, right? So first element is 4. So 4 is root. So you remember what will be the first element in pre-order? Root of a tree. So 4 is the root of a tree. So search for 4. Search, it is found. Observe once again. Search for 4 in this list of elements. Yes, it is found here. So take 4 in one node. This is root. Then what about the rest of the elements? 7, 6, 9, 3 on the left hand side of 4. 7, 6, 9, 3 on the left hand side. And these elements on the right hand side, 5, 8, 2, 1. So 5, 8, 2, 1 on the right hand side. Yes, we got first node, that is first root node. If I tell you this step once again, first element, search, then split. Move to the next element, 7. Search for 7, then 7, where it will be, on the left hand side or right hand side? See, as per pre-order, will be going on left hand side. If it is not found, then we'll go on right side. So search in left hand side. Yes, 7 is found. 7 is found. Then split. 4 was already there. Then left hand side, left child is 7. Now other elements, 6, 9, 3, all of them are on the right hand side of 7. So okay, take them on in a single node on the right hand side of 7. This part is as it is. So searching and splitting. Now let me do the rest of the nodes quickly. Next element, 9. Search. It is found either in this list or this list. This list found. Split. So here I will draw 4 on this side, then 7 on the left hand side, then 9 is on the right hand side of 7. Then what about the remaining elements, 6 and 3? They are on the different sides of 9. So left hand side take 6, right hand side take 3. Yes, 6 on this side, 3 on this side. This is completed. Then right hand side elements are as it is, 5, 8, 2, 1. 5, 8, 2, 1. Then move to the next element, 6. Search, it is found here. And that's a single element. Yes, we want single element only. So it's perfect, don't do anything. Next, 3. 3, search for 3, it is found here. And it's a single element. Don't do anything. Next element, 2. Search, it is found here. Found here. So there are more than one element. So split. So I will draw here. So this side is already completed. So I will take it as it is. And here, new root is 2. 2. So 5 and 8 on the left hand side. 5 and 8. On the right hand side, 1. Yes. Next, move on to the next element. That is 5. Search for 5. It is found here. Yes, 2 elements are there. So split. I will draw it here. So 4. So this left hand side is as it is. Right hand side 2 and 1 as it is. Then this node I have to take 5. Okay, take 5. What about 8? Where it should be? It is on the right hand side in a node. So it will go on the right hand side only. So this is on the right hand side. Continue. 8. Search for 8. Single element. Don't do anything. Move next. 1. Search for 1. Found. Single element. That's all. This is a tree. This is a unique tree. Just one single tree. For this tree, this is the pre-order and this is the in-order. There is no other tree possible which gives same pre-order and in-order. So this is a unique tree. So we are able to generate a unique tree if pre-order and in-order is given, and this is the procedure. See, this was the first step, and in the second step we have taken 4, and the third step we have split at 7 because we were moving along from left hand side to right hand side. We were scanning pre-order from left to right. Then fourth step we have taken 9, so automatically got 6 and 3 also. So this also completed. Then next, here we selected 2. This was 4th, 5th, 6th. Then this is 7th step, I should say. So in this step 2 was splitted. Then 8th step, in this 5 was splitted. So even 8 was also splitted. We got a tree. This is the procedure. Now analysis. What is the time complexity? How much time it is taking? So actually we have done board work. We have not written any code or the pseudocode or algorithm. Just based on the procedure only we have to give the time. So what was the work done? We have scanned through pre-order. All the elements we have scanned through them once. So this is n. Yes. But while scanning for every element, what we were doing, searching for that element here to make it as root or make it as a new node. So we were searching for the element every time. So for every element we were searching. So searching takes how much time? N time. So how many times we have searched? For every element we have searched. So n into n, right? Searching is taking n times, right? Search takes n time. And how many times we have done? For n elements we have done. So there are n elements. So n element search for n times. So this is n square. So the time taken by this procedure is n square. So that's all about this procedure. So generating a tree from traversals is very important. I will show you the program for this one. Yeah, in this video we'll learn about a function for counting nodes in a binary tree. So already I have an example binary tree and also a function available, and this function is recursive. So just I will explain how this function works. Let us trace the function to understand the working of a function so that you can write down similar functions if you require. Let me read out this function and explain few things, then I will show you tracing. Function name is count, and I have taken some temporary variables x and y. These are local to a function. Pointer name is p. That should be a root node pointer. If p is not null, then count itself upon left child, count itself upon right child. Get the result of left child in x, get the result of right child in y. So two function calls, on left child also, right child also. Then for counting every node, plus 1 should be added for every node, right? First node, second node, third node, one by one you have to go on adding. So where adding is done, whatever the result of left hand side plus whatever the result of right hand side plus 1, this node. Number of nodes on left side, number of nodes on right side, then plus 1, this node. So I have just read it out, so it makes sense that this is counting the number of nodes and it is doing recursively, it is calling itself. If p is not null, do all these things. If it is null, else part, this is else part. I don't have to write else because if itself is having a return, so I don't have to write else. Even you can write else, then inside that you can write this, return 0. Means if there is no node, if it is null, then return 0. Then one important thing I have to show you. Counting of a node is done in this line, in this statement. Just look at this. And before counting, it is going on left child and right child. So first left, then right, then count. I'll change it. Just listen. First left, then right, then print. What is this? First left, then right, then print. This is post order. Yes, this procedure or this function is working in post order form. This is working in post order form. And one thing I will tell you, what all the processing you want to do upon binary trees, most of the time you have to use post order form. So post order is more commonly used upon binary trees for doing any type of processing. So now let me trace this and show you. So already you know how recursive function works, so I will not spend much time. Quickly I will show you tracing. So I am showing you tracing upon tree directly. So first root, function is called upon root. Then root is not null, yes, not null. What are the steps when it is not null? 3 steps are there. Find x, find y, then add them plus 1 and return. So first find x. Call on the left child. First finish first step, then you go on second step, y. First finish first step. First step go on left child means it will come on this node. Upon this node, this is not null, so again x assign. Call upon left child. Whatever the result you get, you take it in x. Okay, again it is called here. So this is not null. On the left side, x assign. Call upon left side. Left side is what? Null. Here left side is null. Here left side is null means what is the result from this one? 0. If it is not null, it is entering here. If it is null, then it will return 0. So from this side, the result will be 0. I'll just extend and show you. This side result will be 0. So this x will contain 0. It has called itself on the left side, which was null. So the value of x is 0 for which node? Node 12. So first step is finished for node 12. Then perform second step. Y is equals to right child. Y is equals to right child. There is a node. So for this new call, fresh call. So again for this node x assign left child. Then for this left child, again it's not null. So x assign left child. So for this left, nothing is there. Null, 0. So this will be 0. Then for right also it is 0. Now for this node 9, two steps are over. First step, second step. Then third step, x plus y plus 1. 0 plus 0 plus 1 is returned. It will go to this node. In which variable? X, because it was called on left side, 1. Then on this side, y. For this side, x. There is nothing, null. So 0. Y, 0. 0 plus 0 plus 1. 1 is returned. Now for this node, the left hand side, x value also it knows, y also it knows. 2. See, I said it is in post order, right? So this left, right completed. Then root. 1 plus 1 plus 1. 3. See, this is giving the number of nodes below this one. Now this is ready. 0 plus 3. 3 plus 1. 4. So 4. Then right side. Y. This is 0. There is nothing on this side. Null. Go back. 4 plus 1. 4 plus 0 plus 1. 5. 5. See below this check. 1, 2, 3, 4, 5. 5 nodes are there. Then go on the right hand side. Then upon this one left hand side, upon this one left hand side, null, 0, right hand side, 0, 0 plus 0 plus 1, 1 goes back to this one. Then on this side, y, left side, x, 0, y, 0, 0 plus 0 plus 1, 0 plus 0 plus 1 goes back, 1. This side, y is a 0. Now these two are added and return 1. So 1 plus 0, 1 plus 1, 2, 2. 1 plus 2, 3, 3 plus 1, 4. Now 5 plus 4, 9 plus 1, 10. So the answer is 10. So that's all. This is working in post order. I'll make one small change in this code, right? Then you have to tell me what this function will do. Here I will write on the statement. If p cap L child and p cap R child, means P's left child is there, it's not null, and right child is also not null, then return x plus y plus 1. Else return x plus y. Then this if ends, this if, and at last return 0. Guess what this will do? This condition. This condition is for both left and right child are there. So it means if both the children are there, then only it will count 1. Otherwise 1 is not counted. Means that node is not counted. So it will count only those nodes who are having both the children. So nodes with the degree 2. From this tree, which nodes will be counted? 8 is having both the children, 4 is having both the children, 5 is having both the children. So only 3 nodes will be counted. So this will count the number of nodes which are having both the children, left side as well as right side. Just I have introduced one condition and it became a condition for counting nodes with the degree 2. Change the condition to count leaf nodes, change the condition to count nodes with the degree 1. Whatever you like you can do. Next, I will make one more change. Return, there are no if else, x plus y plus p's data. Can you tell me what will happen? P's data is added. Yes, it will add all these elements from a tree. You will get the sum of all the elements in a tree. Then student exercise. Here I am modifying the code. So don't know what the function is doing. Okay. Function name I will call it as fun. And this is fun is calling itself. Fun is calling itself. I am modifying it. If x is greater than y, return x plus 1. Else return y plus 1. Take this and find out what this function is doing. Right? What this function is doing. It's not adding x and y both. Either x plus 1 or y plus 1. So for understanding or knowing what that function is doing, you have to trace it upon a tree and observe your result, then you can find out. So for example, you can take this tree there, right? If you take just 2-3 nodes, you may not be able to figure out what it is doing. Take this type of tree and trace that one and find the answer. So that's all. We have seen various functions upon a tree. I have started with the counting, but I have also shown you different functions on this one. In this video, we will write a recursive function for counting the number of nodes in a binary tree, and also we'll write a recursive function for finding the height of a binary tree. This project is same project that we have used for creating a tree, performing traversals, and also for level order traversal. Same program I am using here. Just here before the main function, I will write on a function for counting number of nodes in a binary tree. So it should take a pointer to a root. So I will name it as root only. Then if root is not null, then it should return call itself count on roots L child plus count itself on roots right child plus 1. Otherwise return 0. That's it. And also I will write a function for finding the height struct node root. If root is equal to 0, that is null, then return 0. Otherwise, I need two variables x and y. These I will assign them to 0 initially. Then call the function recursively upon left child, that is roots L child, and y height roots right child. Then whichever is greater, if x is greater than y, return x plus 1, otherwise return y plus 1. That's all. This is for finding height, and also we have written a function for counting nodes. Printf, I will display first count. So call the function count and root. Then printf height percentile d height of root. Now let us run this program and see. Create a tree. So root is 10, left child is 20, right child is 30, 20's left child is 40, 20's right child is 50, and 30 is not having any children, 40 is not having any children, 50 is having a child, 60, and right child is not there, 60's left child and right child are not there. So the number of nodes I have created are 6 and the height is 4. So you can draw this tree on paper and check it, and you can enter the values and verify the results written by this functions, that is count and height. So try this program by yourself. Already we have seen it's working and everything on whiteboard. So this is just a demonstration, so you can practice this program. That's all in this video. In this video, we will see how to count leaf nodes and non-leaf nodes, or the nodes with a degree 0, nodes with a degree 1, or nodes with a degree 2. See, for this example tree, these are leaf nodes, right? These are leaf nodes, and these are all non-leaf nodes. So these are with a degree 0, so these are leaf nodes, and degree more than 0, they are non-leaf nodes. And these are with a degree 2, this is degree 2, right? And this is degree 2. And these nodes are with a degree 1, this is 1, right? And this 1. So that's what we want to count them. We have already seen a recursive function for counting the number of nodes, and this was the function. Already I have shown you the tracing of this one. Now in the same function, if I modify, make some changes, I can count leaf nodes. So let us make changes for various types of nodes. So first one is leaf nodes. See, when do you say a node is leaf nodes? If left child is null and right child is null. So I will remove this line. Okay, I'll remove this line, and here I will say if nodes left child is null as well as right child is null. So P's L child is equals to null. if it is null, as well as P's R child, right, is equals to null. Then if both are null, then I will count that node. So I will return x plus y plus 1. Otherwise, means if any one of the condition fails, then it will not enter here. Then what I should return? I should return x plus y. That's all. See, if these are true, then add 1. Otherwise, don't add 1. So it will add 1 only for those nodes whose both left and right child are null. So this will be counting leaf nodes. And after this if, we can return 0. Means if a node is null, return 0. So this is already there. We have already seen it. So just by adding one condition in the same function for count, we can change this function for counting leaf nodes. So leaf nodes are with a degree 0. So this function is for counting nodes with a degree 0. Next is counting nodes with a degree 2. So what changes I have to do? So inside this function, I should say P's left child is not equal to null and P's right child is also not equal to null. If both are not null, then these are nodes with a degree 2. So this node or this node or this node. So for this tree, I will get the result as a 3. There are 3 nodes with a degree 2. This is for finding nodes with a degree 2. So just change of condition, that is sufficient. So if this is true, both left child and right child, both are there, count. Otherwise don't count. Then third one, counting nodes with a degree 2 as well as 1. Means if a node is having any one child, count it. Means this node should be counted because this is null but this is not null. This is not null, this is null. Both are not null. So for that, I simply have to change this condition as OR. Now, this works for counting nodes with a degree 1 and 2. So all internal nodes. So that's it. This is sufficient. Now next I will show you how to write the condition for counting those nodes whose degree is 1. So only it's a matter of changing the condition. So I will remove this function and here I will write down all the conditions for leaf node, non-leaf node, all the conditions I will write down. So let us see the conditions. See, first one, leaf node condition. So leaf node condition, if a P's left child, right, is equal to null. So for that I can write not, as well as P's right child should be equal to null. So for that I can write not. This is for leaf node. And node with the degree 2. So here condition is if P's L child is not equal to null. So I don't have to write anything. So it is not equal to null only. We have already learned about this one, right? The next is P's R child. If both are true, then this is for degree 2. Then the third one, degree 1 or 2. So for this, the condition is if P's left child is not null or P's right child is not null. This is the condition. This is for exactly degree 0, right? Exactly degree 2. This is 2 or 1. Then last one, exactly degree 1. So exactly degree 1 means if it is not having left child, it must have right child. Or if it is having left child, it should not have right child. This is the condition. So for that, I will write down the condition here. That is fourth condition for degree exactly 1. So the condition is if P's L child, right, is not equal to null, then and definitely P's R child should be equal to null. Right? This is one condition. So I'll put it in bracket. Or the second part, or if a P's left child is null, then this should not be null. So I will write down, in the next line I will write down, P's L child is equal to null. See, earlier we have written not equal to null. Here I have written not equal to null. So now it is equal to null. And P's R child should not be equal to null, right? R child not equal to null. This is how we can write on the condition for exactly one child, that is degree 1. See, this is too much lengthy. Can't we reduce the size? See, this is very lengthy condition. This is a condition continuation from here to here as a single condition. This also should be in the bracket. This is very lengthy. Can't we reduce it? So I'll remove this and show you how I can reduce this one. So this you can take it, if you want to note down, you can note down this one, right? This one I will write once again. This one is just like, if left child is there, then right child should not be there, right? This part. Or if left child is not there, right child must be there. Left child is not there, right child must be there. So what is this? This is nothing but L exclusive or R. L exclusive or and R. So this is with left and right are exclusive or. So is there any exclusive or operation in C, C++, right, like languages? Yes, they have. What is that? So I will write down this condition once again here. So here, if P is L child, right, is not equal to null. This is L. XOR P is R child not equal to null. This is R. Yes, this caps is a symbol used for exclusive OR. So I have reduced this lengthy condition into a simple condition like this. So this is the condition for degree 1. So that's all. We have finished with all various type of conditions. Now count function I have shown you by using x and y variables. It can also be written without using those variables. So it can be written in a simple form also. So I will show you the other ways how you can write down the same recursive function only. So I'll write down the function. See, function name is count. So I will call it as count only, which is taking a pointer to a node, struct node pointer P. See, I will not take any variables x and y. Simply first I will check the condition. If P is equal to null, means if it is null, we know well that if it is null, then return 0. Okay, this is over. Else I don't have to write, because inside the condition there is a return statement. So if it is true, it will return, function will stop, it will never come here. So I can write on the code without writing else. So let us see. Just say return count P is L child, right, plus count P is R child plus 1. That's all. This is so simple. See, left child, right child plus 1. Earlier I was taking these values in x and y variables, then I was adding 1. So now it can be written directly. I am calling the function and the right child also calling the function plus 1. So the working will be same. So this is another way you can write on this one. Then regarding leaf node, non-leaf node, here I should have a condition. That is, if it is a leaf node condition, plus 1. Otherwise, one more time I should write down count left, right, and without writing plus, I should write down. See, for example, here I will write if PL child and PR child not, so this is for leaf node condition, add 1. Otherwise, return count P is left child plus count P is right child. That's all. So this is the count function. So we have learned how to find the number of leaf nodes and the number of non-leaf nodes. So you can practice this program.